What if the universe is not just a vast, seemingly infinite expanse of stars, but rather a realm brimming with unsolved mysteries, an intricate tapestry of cosmic phenomena, many of which remain completely beyond our comprehension? From the enigmatic whispers of black holes to the terrifying allure of rogue planets, the cosmos is filled with phenomena that continually challenge, confound, and redefine our understanding of reality itself. One of the most striking and mind-bending phenomena in this strange world are black holes. These are not just voids or empty spaces, they are some of the most enigmatic and dangerous objects in the cosmos. A black hole is, in essence, a region in space where gravity is so powerful that nothing, not even light, can escape. This phenomenon occurs when an enormous amount of mass is compressed into an incredibly tiny area. To visualize this, imagine squeezing the mass of an entire star into a point so small that it defies all understanding. The concentration of mass in such a small volume distorts the very fabric of space and time around it, creating an intense gravitational pull that is not only difficult to escape, but also incomprehensibly powerful. What makes black holes particularly fascinating, and indeed terrifying, is the way they challenge the very foundations of our understanding of the universe. When an object ventures too close to a black hole, it passes a point of no return. This boundary, known as the event horizon, is an invisible line that marks the limit beyond which nothing can escape. Once an object crosses this line, it is pulled inward, trapped forever by the black hole's gravity. To make things even more eerie, anything that crosses this boundary, whether light or matter, appears to vanish from our observable universe, as if it has been erased from existence. The result is a haunting aura of mystery surrounding these cosmic giants. The sheer scale and power of black holes are staggering, with their size and mass varying dramatically. Stellar black holes are formed when massive stars collapse under their own gravity, while supermassive black holes, which can be found at the centers of galaxies, can contain the mass of millions, even billions, of suns. These supermassive black holes can cause violent interactions with nearby stars and gas clouds, creating immense bursts of radiation that shine brightly across vast distances, visible to telescopes far and wide. The combination of inescapability, immense gravity, and destructive potential makes black holes some of the most captivating yet terrifying phenomena in the cosmos. They are the limits of our understanding, pushing the boundaries of physical laws and offering a chilling reminder of the immense, often hostile forces that shape the universe. Yet black holes are far from the only cosmic mysteries that challenge our perceptions. Another fascinating, albeit equally mind-blowing phenomenon is the neutron star. Born from the catastrophic death of a massive star in a supernova, neutron stars are one of the universe's most extraordinary and paradoxical creations. When a star, at least 8 times the mass of our sun, reaches the end of its life, it can no longer support itself against the pressure created by gravitational collapse. As the star's outer layers explode outward, the core contracts, collapsing under its own gravity. In this process, protons and electrons combine to form neutrons, creating a densely packed core composed almost entirely of these subatomic particles. This incredibly rapid transformation happens within mere seconds, leading to the birth of a neutron star. The result of this violent collapse is a small but incredibly dense object. To put it in perspective, a neutron star can possess more mass than the sun, but is packed into a sphere no larger than a city. The matter within a neutron star is so densely packed that the space between its atoms disappears entirely. It is a place where the normal rules of matter break down, as the strong nuclear forces binding neutrons together create a compression so extreme that the concept of space as we know it seems almost irrelevant. The density of neutron stars is mind-boggling. In fact, just 1 teaspoon of material from a neutron star could weigh as much as an entire mountain here on Earth. But density isn't the only mind-bending feature of neutron stars. These objects also possess incredibly powerful gravitational forces. The gravity surrounding a neutron star is so intense that it can warp space and time itself, bending the very structure of reality around it. It's as if the laws of physics themselves are stretched to their breaking point, offering us a glimpse into the most extreme conditions imaginable in the universe. Both black holes and neutron stars are stark reminders of the universe's strange, often hostile nature. They exist at the boundaries of what we can comprehend, representing both the power and the mystery of the cosmos. As we venture deeper into the unknown, we uncover new questions, and with each new discovery, we come closer to understanding not just the cosmos, but the very fabric of reality itself. Neutron stars born from the explosive death of massive stars in supernova events are among the most intriguing and extreme objects in the universe. These stellar remnants are characterized by their extraordinary density and intense gravitational forces, which warp the very fabric of space and time. When a star with a mass greater than and about 8 times that of the Sun reaches the end of its life, it collapses under its own gravity, resulting in a neutron star. Despite their small size, typically no larger than a city, they possess a mass several times that of our Sun. Their density is so remarkable that a single cubic centimeter of neutron star material would weigh as much as a mountain here on Earth. As neutron stars spin at incredible rates, they emit beams of radiation from their magnetic poles. These beams sweep across the cosmos, and when they point in our direction, they can be detected as pulsars. Pulsars are highly magnetized, rapidly rotating neutron stars that emit regular bursts of radiation, often in the form of radio waves. The regularity of these emissions, similar to the ticking of a cosmic clock, makes them incredibly useful for scientists studying the fundamental laws of physics. As the beams sweep through space, they mark the rotation of the neutron star itself, providing invaluable insight into the extreme conditions under which these stars exist. What makes pulsars so fascinating is not just their ability to shine like cosmic beacons, but the extreme physics governing their behavior. These neutron stars spin so rapidly, sometimes completing a full rotation in just a few milliseconds, that they generate an environment that challenges our understanding of space, time, and gravity. The gravitational field around a pulsar is so intense that it causes space and time to warp dramatically. This warping provides a unique testing ground for Einstein's theories of general relativity, allowing scientists to study the behavior of matter under extreme conditions. Additionally, pulsars possess magnetic fields that are billions of times stronger than Earth's, and this immense magnetism interacts with their rapid rotation in a variety of fascinating ways. In some cases, pulsars experience glitches, where the timing of their pulses suddenly shifts. These glitches challenge our models of stellar physics, suggesting that the interiors of neutron stars may behave in ways that we have yet to fully understand. Observing pulsars, therefore, provides critical clues not only about neutron stars themselves, but also about the fundamental nature of matter and gravity in the universe. In the same family as neutron stars, magnetars are an even more extreme and fascinating phenomenon. Formed from the remnants of a supernova explosion, magnetars are neutron stars with magnetic fields that are orders of magnitude stronger than those of typical neutron stars, sometimes 1,000 times more powerful. To put this into perspective, their magnetic fields are trillions of times stronger than Earth's magnetic field. This immense magnetism profoundly impacts the star's immediate surroundings, generating intense radiation, particularly in the form of X-rays and gamma rays. Imagine the power of a magnetar as akin to a cosmic lighthouse, its magnetic field sending out pulses of high-energy radiation across the universe. These energetic pulses can be detected from vast distances, offering scientists a glimpse into the powerful forces at play within these stellar remnants. The energy emitted by a magnetar is so powerful that it can affect the very fabric of space itself. The star's magnetic field influences the motion of charged particles in its vicinity, guiding them along its magnetic field lines and creating jets of high-energy particles that shoot out into space. This process is not limited to radiation alone. The intense forces at work can also have physical consequences on nearby celestial bodies. For instance, a magnetar's powerful magnetic field can distort the environment of any planets or stars that find themselves nearby. This distortion can trigger phenomena like auroras, just as Earth's magnetic field generates auroras near the poles. However, the consequences are far more severe, with magnetars capable of influencing or even tearing apart nearby stars and gas clouds. While pulsars and magnetars are examples of how neutron stars operate, the universe also harbors a more theoretical construct known as a white hole. These cosmic entities present a stark contrast to black holes, offering a speculative, albeit captivating idea in astrophysical research. Black holes are infamous for their ability to trap everything that comes too close, including light, which is why they are invisible to our eyes. White holes, on the other hand, are thought to expel matter and energy rather than draw it in. Picture a black hole as a funnel, pulling everything into an irreversible abyss, while a white hole is imagined as a fountain, expelling matter and energy into space, never allowing anything to fall back in. While black holes represent a sink for matter and energy, white holes theoretically serve as the opposite, an ultimate release. They remain entirely hypothetical, and no white hole has ever been observed in the universe. Some theories suggest that white holes might be connected to black holes via a wormhole, creating a bridge between two vastly different regions of space-time. Though entirely theoretical, the idea of white holes pushes the boundaries of our understanding of the cosmos and challenges our models of time, space, and matter. Equally intriguing are rogue planets, planets that do not orbit any star but instead drift through space, isolated from the gravitational pull of a parent star system. Rogue planets are formed in much the same way as regular planets, coalescing from gas and dust in a protoplanetary disk. However, they are ejected from their parent systems during their formation due to gravitational interactions with other massive objects, such as neighboring planets or passing stars. As a result, rogue planets wander through the dark voids of space, entirely independent of any star. Their only source of heat is residual warmth from their formation or internal processes, as they receive no energy from a central star. The existence of rogue planets presents a paradox for astronomers. These planets are often thought to be rare, yet recent studies suggest that there may be as many, or even more, rogue planets in the galaxy as there are stars. This raises fascinating questions about planetary formation and stability, especially since most models of planetary systems assume that planets form around stars. Rogue planets defy this model, offering a new lens through which to study the dynamics of planetary systems. The isolation of these planets might seem inhospitable to life as we know it, yet they spark curiosity about the potential for life to exist in extreme conditions. In contrast to the smaller bodies like rogue planets, supermassive black holes are colossal entities that lie at the centers of most galaxies. These immense objects hold a key position in the structure and behavior of their host galaxies, exerting gravitational forces that shape the stars and gas clouds around them. Imagine a supermassive black hole as a cosmic anchor, holding its galaxy together and influencing its entire structure. These black holes can have masses billions of times greater than the Sun, and their gravitational pull affects the movement of stars and interstellar gas. Supermassive black holes also play a critical role in galactic evolution by feeding on matter from their surroundings. As matter spirals into a supermassive black hole, it forms an accretion disk, a rotating disk of gas, dust, and other matter. The material in this disk heats up to extreme temperatures as it is pulled toward the black hole, emitting bright radiation in the process. This radiation is one of the brightest phenomena in the universe, often visible from great distances. Interestingly, the energy released by a supermassive black hole can influence star formation within its host galaxy. The intense radiation from the accretion disk can heat up surrounding gas clouds, preventing them from cooling and condensing into new stars. In some cases, this feedback mechanism can actually suppress the birth of new stars, shaping the galaxy's overall evolution. The universe, it seems, is a place of extremes, where massive forces and extraordinary phenomena push the limits of our understanding. Whether in the form of pulsars, magnetars, white holes, rogue planets, or supermassive black holes, these objects reveal a universe far more complex and mysterious than we can even begin to fathom. As our technology and theories evolve, we continue to uncover new layers of cosmic wonder, each discovery leading to more questions and ever more fascinating possibilities. Furthermore, supermassive black holes possess a truly remarkable ability. They can generate powerful jets of particles that shoot outward at nearly the speed of light, These energetic jets can stretch far beyond the confines of their host galaxies, extending into the vast emptiness of intergalactic space. As these jets interact with the surrounding medium, they have the potential to influence not just their own galaxy, but neighboring galaxies as well. The shock waves created as the jets collide with surrounding gas can compress material, triggering a cascade of effects that can lead to the formation of new star clusters. In this way, supermassive black holes are far from passive entities lurking in the centers of galaxies. They are active, dynamic forces that play a crucial role in the evolution of their host galaxies. Their influence is not limited to their gravitational pull, which is strong enough to alter the very fabric of spacetime itself. These black holes create a delicate yet powerful balance between the immense forces of gravity and the high energy release of radiation. This interplay of forces can either promote or inhibit the formation of stars, all while continuously reshaping the structure of the galaxy over time. This relationship between supermassive black holes and their host galaxies is a stunning reminder that black holes are not just cosmic vacuum cleaners, devouring everything in their path. Instead, they are integral players in the life cycle of galaxies, influencing their growth, structure, and evolution in profound ways. The impact of these black holes can be seen in the way they regulate star formation, creating environments where new stars can be born, while simultaneously preventing the collapse of existing stellar systems. Among the most astonishing phenomena in the cosmos are quasars, or quasi-stellar objects. To truly appreciate these marvels of the universe, we must first examine their connection to supermassive black holes. Found at the centers of many galaxies, quasars are essentially the brilliant, high-energy cores of distant galaxies, powered by the relentless accretion of material into a supermassive black hole. This material, often composed of gas and dust, spirals inward toward the black hole, forming an accretion disk, a swirling mass of particles that heats up to extreme temperatures due to friction and gravitational forces. As this material is consumed by the black hole, it releases an immense amount of energy, far exceeding the energy output of the galaxy as a whole. The result is a phenomenon so intense that it can outshine entire galaxies, emitting light that is billions of times more powerful than that of our own sun. The sheer brightness of a quasar is further amplified by the vast distances that separate us from these distant cosmic objects. As light travels across the vastness of space, it can be stretched and dimmed, which makes the quasar's light appear much more luminous than the light from stars in our own galaxy. This phenomenon allows astronomers to study quasars from such great distances, giving us a rare glimpse into the distant past of the universe, often billions of years ago. In addition to the visible light they emit, quasars radiate energy across the entire electromagnetic spectrum. This includes not only visible light, but also radio waves, ultraviolet light, and even X-rays. This broad emission of energy across multiple wavelengths allows scientists to study quasars in great detail, revealing the complex processes at work within the heart of these distant galaxies. The study of quasars not only deepens our understanding of supermassive black holes, but also provides a window into the early universe, helping us to understand how galaxies and black holes evolve over cosmic timescales. Ultimately, quasars and supermassive black holes are linked in a dynamic and awe-inspiring relationship. These cosmic powerhouses are not mere relics of the past. They continue to shape the universe in ways that we are just beginning to comprehend. Their influence extends far beyond the boundaries of their own galaxies, making them key players in the ongoing evolution of the cosmos itself. Moreover, quasars emit energy not only in the form of visible light, but also across the entire electromagnetic spectrum, from radio waves to ultraviolet light and even X-rays. This extraordinary range of emissions makes them not only powerful beacons in the vast expanse of the universe, but also objects of intense fascination for astronomers. Their ability to shine so brightly in a multitude of wavelengths allows them to serve as critical tools for exploring the distant reaches of space. These enigmatic objects provide invaluable insights into the formation and evolution of galaxies, offering a glimpse into the conditions that shaped the universe as we know it. In essence, quasars act as a window into the distant past, revealing the complex processes that took place in the early universe, long before galaxies took the familiar forms we see today. At the same time, another extraordinary feature of the cosmos emerges: cosmic strings. These are theoretical structures that intrigue scientists and challenge our understanding of space-time. Imagine, if you will, these cosmic strings as incredibly thin, one-dimensional filaments that stretch across the universe like threads woven through the very fabric of existence. They are not mere curiosities, but key players in shaping the universe on a grand scale. It is as though, instead of simply holding material together like seams on fabric, cosmic strings profoundly alter the structure of space-time itself. These strings are believed to have formed during the earliest moments of the universe, a period when conditions were both extreme and chaotic. As the universe cooled and expanded, certain regions experienced phase transitions that resulted in the creation of these cosmic structures. What makes them even more fascinating is their immense density, which is so powerful that their gravitational influence can warp the surrounding space-time. Picture, if you will, a heavy bowling ball placed on a stretched rubber sheet. The way the fabric of the sheet bends under the ball mirrors how cosmic strings bend space-time. The presence of cosmic strings challenges the very foundation of our understanding of space-time. For one, they can induce remarkable gravitational effects, including the bending of light. This phenomenon, known as gravitational lensing, occurs because the path of light is not determined solely by the mass or distance of objects, but can be significantly influenced by the gravitational field of these cosmic strings. The presence of these structures introduces a bizarre dimension to the behavior of space-time itself, often leading to phenomena that were once thought to be purely theoretical. For example, the warping of space-time around cosmic strings can create closed time-like curves, paths through space-time that might, in theory, allow for time travel. This tantalizing concept raises profound questions about the nature of causality and time itself, suggesting that the universe might be far more complex than we have ever imagined. Moreover, the study of cosmic strings could eventually lead to groundbreaking discoveries about the forces that govern our universe. They may be connected to theories that attempt to unify the fundamental forces of nature, such as gravity and electromagnetism. In unraveling the mysteries of these cosmic structures, scientists may gain access to the deepest secrets of the cosmos, bringing us closer to understanding the origin and fundamental laws of the universe. Cosmic strings, with their mind-bending implications, remind us that there is still so much we do not know about the fabric of reality. Meanwhile, galaxies themselves are vast, majestic structures that form over billions of years through the slow accumulation of gas, dust, and dark matter. In the earliest days of the universe, tiny fluctuations in the density of matter created regions of higher mass. These regions attracted more matter due to gravity, gradually forming clumps that would grow larger over time. These clumps merged, giving birth to the first stars. As these stars shone brightly and lived out their short lives, they expelled heavy elements into the surrounding gas, enriching it and providing the building blocks for the next generation of stars and planets. As galaxies evolve, they present both beauty and terror. While they are breathtaking in their vastness and intricacy, they also harbor some of the most dangerous and mysterious features in the universe. At the heart of many galaxies lies a supermassive black hole, often millions or even billions of times the mass of the sun. These black holes exert such an immense gravitational pull that not even light can escape once it crosses the event horizon. Anything that ventures too close risks being consumed. The regions near these black holes are among the brightest and most dangerous in the cosmos, as the gravitational forces can create accretion disks of gas and dust that spiral inward, heating up and emitting powerful radiation. In addition to the dangers of black holes, galaxies are also embroiled in a process known as galactic cannibalism. This occurs when a larger galaxy attracts and absorbs a smaller one, merging their stars, gas, and dark matter. Such mergers can lead to violent interactions that disrupt existing star systems and can trigger new waves of star formation, but also result in cosmic chaos. The dynamics of these mergers are complex, creating both beauty and havoc as galaxies collide, their contents blending in spectacular and often catastrophic fashion. Galaxy clusters, which are vast groups of galaxies bound together by gravity, add another layer of intrigue. These clusters can harbor dark matter halos, invisible but incredibly powerful regions of dark matter that influence the movement of galaxies within the cluster. The environment within these clusters is often hostile, with galaxies frequently interacting in ways that can disrupt and even destroy star systems. These interactions can also lead to the formation of massive jets of gas and energy, extending outward into the vast emptiness of space, as galaxies clash in a cosmic drama that plays out over millions of years. Amid all this chaos, the Great Attractor looms, a mysterious region of space that exerts a gravitational pull on galaxies in our cosmic neighborhood. Imagine this area as a colossal mass hidden behind the Milky Way, pulling neighboring galaxies into its gravitational web, creating what can be described as a cosmic traffic jam. Despite its profound influence, astronomers have struggled to pinpoint its exact nature and structure. The dust and gas of the Milky Way obscure our view, preventing us from directly observing the Great Attractor. However, its existence has been inferred by studying the movement of galaxies in its vicinity. Located in the direction of the southern hemisphere, within the constellations Centaurus and Hydra, the Great Attractor is part of a larger structure known as the Laniakea supercluster, a vast network of galaxies and dark matter filaments that stretch across the universe. As we delve deeper into this enigma, it raises profound questions about the distribution of mass in the universe. What exactly is the source of the gravitational pull exerted by the Great Attractor, and how do these immense structures affect the cosmic dance of galaxies? The more we learn, the more we realize that the universe is filled with mysteries that continue to challenge our understanding of gravity and cosmology. The dynamics of galactic collisions further illustrate the complexity and beauty of the universe. When two galaxies approach each other, their mutual gravitational attraction sets in motion a series of events that can completely alter their structure. Over the course of millions of years, the gravitational influence of the two galaxies can distort their shapes and trigger dramatic changes. As these colossal entities collide, the pressure exerted on their gas, dust, and stars can lead to the formation of long, stretched-out tidal tails, streams of stars and gas that extend like cosmic ribbons. These phenomena create stunning visual displays, while also sparking the creation of new stars in what are known as starburst events. The intense gravitational forces involved in these collisions can compress gas clouds, causing them to collapse and trigger new waves of star formation, brightening the galaxies in a blaze of light. Such cosmic events not only captivate the imagination, but also remind us of the raw forces at play within the universe, forces that continue to shape the vast, ever-changing landscape of galaxies and beyond. When two galaxies collide, it's not just a simple merging of stars and gas. The process is far more chaotic and dramatic than we might imagine. The gravitational forces at play during such a cosmic clash are so immense that they lead to profound structural transformations. As the galaxies spiral toward each other, they don't just combine seamlessly. Instead, the interaction often results in the birth of an entirely new galaxy. The central regions of these merging galaxies may spiral inwards, drawn by their mutual gravitational attraction, and in many cases, this results in the formation of a massive, supermassive black hole at the heart of the new cosmic entity. While astronomers and cosmologists have made impressive strides in simulating and observing these galactic collisions, capturing every facet of these dramatic events is still elusive. The process is far more complex than current models can fully represent, mainly because of the numerous hidden variables at play. Dark matter, for example, remains a significant enigma. It's not just its gravitational effect that complicates our understanding, it's the precise dynamics of the stars within these galaxies, the way they interact, and the behaviors of the gas that are still being studied in great detail. Each of these factors introduces an added layer of complexity to the already turbulent event of galactic collisions. The aftermath of such a colossal encounter is equally complex. The shockwaves sent through space can disrupt not only the galaxies themselves, but also the planetary systems within them. The stability of existing habitable environments can be severely affected, raising questions about the long-term sustainability of any life that might reside there. It's an illustration of the unpredictable nature of the universe, where chaos and order, beauty and devastation coexist in a delicate balance. And as we advance in our technological abilities and improve our observational tools, we get a little closer to unlocking the mysteries of these grand cosmic events. Dark matter, in particular, presents a whole new set of challenges for scientists. Unlike the familiar galaxies made up of visible matter, such as stars, gas, and planets, dark matter operates on a different set of principles. The most striking difference is that dark matter does not consist of atoms in the same way ordinary matter does. As a result, it doesn't emit, absorb, or reflect light, making it invisible to our telescopes. This absence of light interaction means that dark matter is hidden from direct observation, which is why it remains such a significant mystery in modern cosmology. To understand the role dark matter plays in the formation and movement of galaxies, we need to think about it as a scaffolding. Dark matter is thought to provide the gravitational influence that helps to hold galaxies together and guides their formation. Inside dark matter galaxies, the gravitational clumping of this invisible material is responsible for the motion of stars. While we can't see dark matter directly, we can infer its presence from its gravitational effects on the galaxies around it. One method astronomers use is to observe the speed at which stars orbit within a galaxy. The velocities of these stars suggest there is much more mass than we can detect, implying the presence of dark matter. However, detecting dark matter is an ongoing challenge. It doesn't interact with electromagnetic forces, meaning it doesn't produce light, heat, or radiation that we can observe. This invisibility makes dark matter a ghostly presence, detectable only by the way it influences other visible objects. Researchers have devised various techniques to study its elusive nature, such as looking for its gravitational pull on nearby galaxies or examining cosmic microwave background radiation for clues. Dark matter's properties suggest it doesn't clump together into dense structures as ordinary matter does, allowing it to exist in a more diffuse state. This allows dark matter to play a crucial role in shaping the cosmos, but also makes it harder to detect. Despite its importance in galaxy formation, dark matter remains a profound mystery. Meanwhile, another colossal feature of the universe, galactic superclusters, exists on an entirely different scale. Superclusters are vast collections of galaxies and galaxy clusters, and they represent some of the largest known structures in the universe. These immense entities are the result of billions of years of gravitational attraction, where vast groups of galaxies are bound together by the invisible forces of gravity. To visualize a supercluster, imagine a grand congregation of stars, gas, and dark matter, all bound together by the unyielding pull of gravity. These superclusters span across hundreds of millions of light years, and light traveling from one end of a supercluster to the other would take hundreds of millions of years. To put this into perspective, a single light year is the distance that light can travel in 1 year, and even that is an unfathomable measure. But in the case of superclusters, the distances are mind-boggling. These structures are not only vast, but they are also dynamic, with galaxies within them often in motion, pulled together by their mutual gravitational attraction. One of the most prominent examples is the Laniakea supercluster, which houses our own Milky Way galaxy. This supercluster stretches across about 100 million light-years, creating a cosmic web of galaxies that are interconnected in ways we are only beginning to understand. When considering the universe on the largest scales, superclusters are only a small fraction of the vastness. In addition to these colossal structures, the universe also contains vast regions known as voids, vast, nearly empty expanses where galaxies are practically non-existent. These voids, along with the superclusters, form a delicate balance, shaping the structure of the universe in ways that are still not fully understood. In fact, the universe, with all its superclusters and voids, resembles a massive cosmic network, a vast web stretching across unimaginable distances, where some regions are densely populated with galaxies, while others remain astonishingly devoid of them. This discovery of a cosmic web structure challenges the early assumption that galaxies would be evenly distributed throughout the universe. Instead, what we find are massive clusters of galaxies, interwoven in a grand network of filaments, with vast empty spaces between them. This web-like structure, consisting of galactic clusters and superclusters, reveals the true scale and complexity of the cosmos. The immense distances between voids and the filaments that connect them form the backbone of the universe, outlining a picture of the universe that is far more intricate than we once imagined. The universe, with its ever-expanding collection of galaxies, dark matter, superclusters, and voids, presents a dynamic, constantly evolving tapestry. It is a testament to the forces of gravity, the unseen pull that shapes the cosmos, that gives it structure and that keeps galaxies, stars, and planets in motion. As we continue to study and observe these vast structures, we find that the universe is not just a collection of isolated objects, but a living, breathing entity, ever-changing and unfolding in ways we have yet to fully comprehend. The universe is a vast and intricate tapestry where the unseen and the unknown play pivotal roles in its continuous evolution. Among the most mysterious and influential forces shaping this cosmic landscape are dark matter and dark energy. Both of these entities, though invisible and imperceptible to our senses, exert tremendous gravitational forces that steer the growth and development of the universe. Additionally, dark matter's presence is fundamental in the grand design of the universe. While it cannot be directly observed, its effects are undeniable. This enigmatic substance, invisible to all forms of detection, serves as a cosmic scaffold that supports the structure of the universe. Through its gravitational pull, dark matter influences the formation of galaxies, galaxy clusters, and other massive structures scattered throughout space. Without it, these formations might never have coalesced into the shapes we observe today. The true nature of dark matter remains one of the great mysteries of modern astrophysics, yet its existence is crucial in understanding the universe's overall architecture. In a sense, dark matter is like an unseen architect, its hands shaping the cosmos, orchestrating the very formation of the structures that fill the observable universe. The implications of its existence are profound. In fact, it suggests that the majority of the universe's mass is shrouded in mystery. The observable matter, the stars, planets, and galaxies we can see and measure, is only a small fraction of the total mass that constitutes the cosmos. This discovery has fundamentally altered our understanding of the universe's composition, revealing that what we see represents just a tiny fraction of what truly exists. Moreover, the universe is far from static. The expansion of space itself is an ever-present force, driving galaxies away from one another, stretching the fabric of the cosmos like an infinite, ever-expanding balloon. This dynamic motion adds another layer of complexity to our understanding, affecting how structures form and evolve over time. But the most shocking revelation in recent cosmology is the fact that this expansion is not just continuing, it is accelerating. What was once assumed to be a gradual expansion, slowing over time due to gravity's influence, is instead being hastened by a mysterious force. This force, dubbed dark energy, has challenged our fundamental understanding of the universe's behavior. The realization that the rate of expansion is not just constant, but actually accelerating, defies expectations. The force of gravity, which normally pulls matter together, should logically slow the expansion of the universe. Yet, dark energy acts in direct opposition to this force, pushing galaxies farther apart with each passing moment. This behavior suggests that dark energy is not merely a passive background force, but an active and dominant factor in the evolution of the cosmos. Scientifically, dark energy is thought to account for nearly 70% of the universe's total energy content, making it a dominant force in the cosmic landscape. Its precise nature remains elusive, but it is theorized to function like a form of anti-gravity. Rather than drawing matter together, dark energy repels, causing galaxies to recede from one another at ever-increasing speeds. As a result, the universe is expanding not just at a constant rate, but with an ever-accelerating velocity. This discovery has profound implications for our understanding of the universe's past, present, and future. The nature of this mysterious force remains one of the greatest unsolved questions in cosmology, but its effects are unmistakable. Imagine for a moment the universe as a balloon being inflated. As more air fills the balloon, the surface stretches, and the space between every point on that surface grows. In much the same way, the universe is expanding, and the distance between galaxies increases. But what drives this expansion? What is the force pushing the universe to grow at such an astonishing rate? That force is dark energy. It operates across vast distances, its influence extending far beyond what we can directly observe. Every moment, galaxies are moving further and further apart, propelled by this enigmatic force. Understanding dark energy is not just a matter of curiosity. It is essential to understanding the ultimate fate of the universe. If the rate of expansion continues to accelerate, what will the universe look like billions of years from now? Will galaxies continue to drift apart until the cosmic void between them becomes so vast that only isolated, distant stars remain? These are the kinds of questions that scientists are grappling with, and the answers could dramatically alter our perception of the cosmos. In addition to these cosmic forces, the universe also contains vast, empty regions known as cosmic voids. These voids are enormous, seemingly desolate spaces scattered throughout the universe. They stand in stark contrast to the dense clusters of galaxies that populate the cosmos, like blank spots on an otherwise detailed map. Imagine a cosmic web where dense knots of matter are connected by delicate threads of cosmic filaments. The voids are the spaces between these threads, gaps in the structure that make up a significant portion of the universe. Some of these voids are so vast that they can span millions of light years in diameter. The existence of these cosmic voids offers profound insights into the universe's underlying structure. When astronomers study these regions, they find that the distribution of matter in the universe is anything but uniform. Rather than being evenly spread out, matter is clustered in galaxies and galaxy clusters, with large, empty spaces between them. This discovery points to a time in the universe's history when matter was far more diffuse and gaseous, before the gravitational forces that we associate with galaxies and stars began to take shape. The voids we observe today are remnants of this earlier, more tenuous stage of cosmic development. These voids also shed light on the large-scale structure of the universe, providing clues about the forces that shaped it. Their existence challenges previous assumptions about how the universe should be arranged. Instead of a smooth, homogeneous distribution of matter, the universe reveals itself to be a complex and dynamic network of densely packed regions and vast, empty spaces. This cosmic web, with its dark matter, scaffolding, and expanding nature, continues to evolve and challenge our understanding of the universe in profound and unexpected ways. As we continue to study these forces, dark matter, dark energy, and cosmic voids, we begin to glimpse the true complexity of the universe. The more we learn, the more we realize how little we know and how much remains to be discovered. The universe is a constantly evolving mystery, one whose grand design is far more intricate than we could have ever imagined. The forces that govern its behavior, both seen and unseen, are shaping its future in ways that continue to defy our expectations. Cosmic voids are among the most enigmatic and fascinating features in the universe, offering profound insights into the fundamental nature of space, time, and the forces that govern cosmic expansion. These vast expanses of emptiness, seemingly devoid of matter, play a crucial role in shaping our understanding of the cosmos. Interestingly, recent research suggests that these voids are not simply empty regions of space, but areas where the influence of dark energy becomes strikingly evident. Dark energy, a mysterious and elusive force believed to drive the accelerated expansion of the universe, permeates all of space, even extending into these seemingly barren voids. As such, the emptiness of cosmic voids serves as a unique and critical backdrop for exploring how dark energy operates on the grandest scales. The universe, in its current state, is not only expanding, but is doing so at an ever-increasing rate. This phenomenon, known as cosmic acceleration, has baffled scientists since it was first discovered in the late 20th century. The presence of dark energy, a force that counteracts the gravitational pull of matter, is thought to be the driving factor behind this accelerated expansion. It's within these immense cosmic voids, regions where matter is scarce and galaxies are few, that dark energy's effects are felt most profoundly. Far from being passive voids of nothingness, these spaces are dynamic environments where the universe's expansion can be studied in its purest form. By examining the properties of cosmic voids, scientists gain valuable insights into both the large-scale structure of the universe and the mysterious forces that govern its evolution. Void studies provide a rare opportunity to understand the grand cosmic blueprint that links galaxies, clusters, and voids together. They are essentially laboratories for examining how the universe expands and how dark energy influences the formation of galaxies, stars, and other cosmic structures. Within these vast regions of emptiness, scientists are piecing together the complex cosmic puzzle that dictates the formation of everything from the smallest galaxies to the largest, most sprawling structures in the universe. By analyzing the behaviors and characteristics of voids, researchers are uncovering new layers of understanding about the forces and processes that have shaped our universe from its inception. Among the most intriguing findings from void studies is how these voids serve as a window into the ongoing cosmic expansion. By studying the void's distribution, shape, and size, scientists are able to map out the overall layout of the universe, identifying patterns that would be impossible to discern in more densely populated regions of space. This allows us to visualize the universe not just in terms of the galaxies and stars we can observe, but as a larger, more intricate system where empty space and matter are intricately connected, both influenced by the same cosmic forces. At the heart of these cosmic structures lie the galaxies themselves, vast collections of stars, gas, dust, and dark matter that form the building blocks of the observable universe. Among the many different types of galaxies, two primary forms stand out: spiral galaxies and elliptical galaxies. Each type represents a unique path of evolution and a distinct approach to cosmic formation. Spiral galaxies, with their majestic, pinwheel-like structure, are often the most iconic. These galaxies are defined by their flat disks, which feature swirling arms radiating outward from a dense central bulge. This beautiful spiral shape is the result of dynamic processes that occur as gas and dust accumulate, cool, and collapse under their own gravity, forming stars within the galaxy's disk. The ongoing formation of stars within spiral galaxies is an essential characteristic that sets them apart from elliptical galaxies. Young stars, shining brightly in regions of active star formation, give these galaxies a vibrant blue hue. As a result, spiral galaxies tend to exhibit a mix of both old and young stars, creating a dynamic and ever-evolving stellar environment. The presence of gas and dust in these galaxies fuels continuous star formation, ensuring that they remain active and luminous over cosmic timescales. In contrast, elliptical galaxies have a more tranquil, settled nature. Often formed through the merger of smaller galaxies, elliptical galaxies tend to have a more rounded, three-dimensional appearance. These galaxies lack the distinct spiral arms that define their spiral counterparts, and instead feature a more uniform distribution of stars. Elliptical galaxies are often home to older stellar populations, which gives them a distinctive yellowish or reddish appearance. Because of their formation history, marked by the gradual accumulation of stars through mergers, the gas in elliptical galaxies is often depleted, halting further star formation. As a result, these galaxies lack the vibrant, active regions that characterize spiral galaxies. Their star populations are older and more evenly distributed, without the contrast of bright, young stars that punctuate the spirals of younger galaxies. Beyond their visual differences, spiral and elliptical galaxies exhibit stark contrasts in their underlying structures. Spiral galaxies, with their flattened disks and organized rotation patterns, are typically less massive than the largest elliptical galaxies. Elliptical galaxies, which can reach colossal sizes, often feature densely packed stars and a more chaotic internal structure. These differences in mass and size also correlate with their distinct evolutionary histories, with spiral galaxies evolving dynamically over time and elliptical galaxies reaching their current form through more passive processes such as galaxy mergers. The formation and evolution of galaxies, whether spiral or elliptical, reflect the dynamic and varied processes that shape the universe on a cosmic scale. Each galaxy tells a unique story of the forces, both gravitational and energetic, that have influenced its structure, its stellar populations, and its place in the cosmic tapestry. Understanding these differences is essential for unraveling the broader mystery of cosmic evolution, providing critical clues about the history and future of the universe itself. As we delve deeper into the cosmos, one of the most captivating and speculative theories regarding the ultimate fate of the universe is the Big Crunch. Imagine the universe as a colossal balloon, expanding ever outward from an initial point of extreme density and heat. The Big Crunch posits that this expansion, driven by the momentum of the Big Bang, will one day reverse. As galaxies drift further apart, the gravitational pull between them could gradually overcome the outward push of cosmic expansion. Over time, this reversal could lead to a slow collapse, pulling all matter back toward a single, incredibly dense point. The final result would be a universe once again compressed into an extremely hot and dense core, potentially giving rise to another Big Bang and starting the cycle of expansion anew. In stark contrast to the Big Crunch is the Big Freeze theory, which suggests a vastly different future for our universe. According to this theory, the universe will continue expanding indefinitely. Galaxies will stretch ever further apart, and the energy required for new star formation will dissipate. As stars exhaust their nuclear fuel, the universe will grow colder, darker, and more desolate. With no new stars to replace the old ones, the cosmos will be left filled with dying stars, black holes, and a general sense of cosmic decay. Eventually, the universe could reach a state of near absolute zero, where the temperature approaches that of a frozen void. While the Big Crunch envisions a dramatic end through collapse and potential rebirth, the Big Freeze paints a more passive, inevitable decline. Both theories offer strikingly different visions of the universe's destiny, and each presents an opportunity for humanity to reflect on its place within the vast expanse of space and time. In either scenario, we are left contemplating the impermanence of existence, the cyclical nature of cosmic processes, and the mysteries of the universe's ultimate fate. Meanwhile, a groundbreaking concept gaining traction in the field of cosmology is that of the multiverse. Imagine the universe as a vast library, where each book tells the story of a different universe, some of which may be strikingly similar to ours, while others diverge wildly. The idea of the multiverse proposes that our universe may not be the only one in existence, but rather one of an infinite number of universes, each with its own set of physical laws and constants. This radical theory emerges from the field of cosmic inflation, which suggests that shortly after the Big Bang, our universe expanded exponentially. During this rapid expansion, bubbles of space-time could have formed, each bubble potentially evolving into a separate, self-contained universe. The possibility of a multiverse challenges our understanding of the universe as unique, suggesting that reality as we know it may be just one of many potential outcomes. Each universe in the multiverse could have its own set of physical constants, such as the strength of gravity or the charge of an electron, leading to a vast array of realities, some of which may be entirely different from anything we can imagine. Understanding the implications of a multiverse raises profound questions about the nature of existence itself. Could there be regions where the laws of physics as we know them are completely unrecognizable? How do concepts like chance and necessity play out in a multiversal framework where multiple universes exist simultaneously, each with its own path of development? These speculative ideas about the multiverse open up new realms of possibility, forcing us to question the very fabric of reality and our place within it. As our understanding of the cosmos continues to evolve, so too will our perspectives on existence itself, stretching the boundaries of what we once thought possible in the realm of science and philosophy. Whether or not the multiverse exists remains an open question, but the very exploration of this concept reflects humanity's insatiable curiosity and drive to uncover the secrets of the universe. The idea of the multiverse brings us face to face with some profound questions that push the limits of both science and philosophy. If there are countless versions of ourselves scattered across different universes, what does that mean for our sense of self? How does it affect the choices we make, our agency, and our understanding of identity? These reflections stretch far beyond personal contemplation. They touch on areas of science that could fundamentally reshape our understanding of the cosmos. Cosmology, fundamental physics, and even the boundaries of observational science are all impacted by this intriguing hypothesis. Although we are still far from being able to test or observe the multiverse directly, the theory stimulates the imagination in ways that challenge the traditional boundaries of scientific inquiry. One of the more fascinating theories to emerge from our exploration of the early universe is cosmic inflation. This theory proposes that in the very beginning, the universe expanded at an almost incomprehensible rate. To picture this, imagine a balloon that inflates not gradually, but exponentially, ballooning out faster than the speed of light in just a fraction of a second after the Big Bang. At this moment, the universe was a seething mass of intense heat and energy, far beyond anything we can experience today. This rapid inflationary phase stretched out tiny quantum fluctuations, minute variations in energy across vast stretches of space, creating the seeds for everything that would later become the galaxies, stars, and structures we observe in the present-day universe. These fluctuations, while minuscule, were critical in shaping the grand structure of the cosmos. Without this brief but intense period of inflation, the universe we see today would look completely different, perhaps lacking the cosmic vastness and the clustering of galaxies that we take for granted. Furthermore, the theory of cosmic inflation also provides an elegant solution to a long-standing puzzle in cosmology. Why is the universe so uniform? Despite its enormous size, distant regions of the universe exhibit strikingly similar properties, even though they are separated by light years of space. According to the inflationary theory, these distant regions were once close together, packed tightly into a small volume before being rapidly spread apart. This rapid inflation explains why the universe, though seemingly vast and diverse, shares an underlying uniformity. Thus, cosmic inflation not only sheds light on the conditions that prevailed in the universe's earliest moments, but also helps us understand the architecture of the cosmos. It bridges gaps in our knowledge and offers a unified framework that links the birth of the universe to the cosmic structures that continue to evolve today. At the same time, another mind-bending concept that has captured both scientific and popular imagination is the idea of wormholes. These theoretical structures act as tunnels or shortcuts through space and time, offering a way to traverse vast distances almost instantaneously. For scientists, wormholes are an intriguing area of research that stems from the principles of Einstein's general relativity. The mathematical equations that describe these phenomena suggest the possibility of these shortcuts, inviting theoretical exploration into their properties, their potential stability, and how they might fit within the known laws of physics. Could wormholes be more than just a theoretical curiosity? In the realm of science fiction, wormholes serve as a gateway to grand adventures and existential challenges. From the pages of books to the frames of films, wormholes represent a way to venture far beyond the reach of conventional space travel, sometimes even facilitating journeys to alternate realities. These imaginative narratives allow us to explore timeless themes such as exploration, the unknown, and the ethical dilemmas that might arise from having access to such extraordinary technology. They tap into our innate desire to discover new worlds, meet alien civilizations, or witness monumental cosmic events. For scientists and storytellers alike, wormholes are more than just a fantasy. They provoke essential conversations about the limits of human understanding and the potential future of space exploration. Whether through rigorous theoretical research or imaginative tales of distant worlds, the idea of wormholes embodies humanity's relentless quest for knowledge and our insatiable desire to explore the unseen frontiers of the universe. Moving from the exotic to the enigmatic, Hawking radiation is one of the most groundbreaking concepts to emerge from the intersection of quantum mechanics and general relativity. Introduced by the renowned physicist Stephen Hawking, this phenomenon challenges our traditional understanding of black holes. Typically, a black hole is envisioned as a region of space with such intense gravitational pull that not even light can escape its grasp. However, quantum theory introduces a fascinating twist to this idea. Space is not truly empty. Instead, it teems with particles that briefly appear and disappear, constantly fluctuating in a process known as quantum fluctuations. Near the event horizon of a black hole, the boundary from which nothing can escape, these fluctuations can lead to strange occurrences. On occasion, a particle and its antimatter counterpart may spontaneously come into existence near the event horizon. If one of these particles falls into the black hole while the other escapes, the escaping particle carries away energy in the form of radiation, known as Hawking radiation. This process suggests that black holes may emit radiation over time, gradually losing mass as a result. It's as though the black hole were slowly losing weight over eons, a process that continues until, theoretically, the black hole could evaporate entirely in a spectacular burst of energy. This idea challenges our long-held beliefs about black holes as immutable objects and sparks new discussions about their ultimate fate and the fundamental workings of the universe itself. In the same vein of extraordinary theoretical ideas, tachyons, hypothetical particles that could travel faster than the speed of light, have captivated the minds of physicists. According to Einstein's theory of relativity, as an object approaches the speed of light, its mass increases, requiring an ever-growing amount of energy to continue accelerating. The idea of tachyons upends this principle, suggesting that these particles could possess imaginary mass, allowing them to exceed the speed of light without violating the laws of physics. In theory, tachyons would move faster the less energy they have, a property that defies our conventional understanding of energy and motion. The existence of tachyons, if proven true, would revolutionize our understanding of space-time and force us to reconsider the limits of speed and energy in ways that could reshape not only theoretical physics, but our very conception of reality. In conclusion, all of these concepts, whether they pertain to the nature of the multiverse, the rapid expansion of the early universe, the mysterious properties of black holes, or the tantalizing possibility of faster-than-light particles, challenge us to stretch the boundaries of our understanding. While we may not yet have the tools to test these theories with the precision we would like, their very existence inspires new ways of thinking and new questions to ask. In doing so, they invite us to rethink what is possible, to look beyond the horizon, and to imagine a universe far more intricate and vast than we had ever thought possible. Moreover, tachyons introduce a profound complication when we examine the principle of causality, the idea that a cause must precede its effect. If tachyons are indeed capable of traveling faster than light, they could potentially create scenarios where an effect happens before its cause. Such occurrences would lead to paradoxes that not only challenge our understanding of time, but also shake the very foundations of reality itself. This concept, though purely hypothetical at this point, provides a tantalizing opportunity for physicists to probe the deepest limits of our knowledge about the universe. The mere possibility of tachyons suggests that the universe may contain hidden aspects that defy our current understanding, forcing a re-evaluation of the fundamental principles of physics and ultimately the nature of space and time. In this sense, tachyons become an intriguing window into realms of physics that remain shrouded in mystery, challenging our perceptions and offering glimpses of potential realities that we have yet to fully comprehend. Even though tachyons are confined to the theoretical, their implications open up avenues for exploring the unknown, pushing the boundaries of both scientific inquiry and our collective imagination. The holographic principle further deepens our exploration of reality, offering a groundbreaking concept that directly challenges the way we perceive the universe. Imagine a two-dimensional surface, a flat sheet, which encodes all the information necessary to describe a three-dimensional space, our entire universe, in fact. According to this theory, the three-dimensional world we experience could merely be a projection of this two-dimensional information encoded onto a distant surface. This projection would function similarly to a hologram, where the 3D image is a product of two-dimensional data. The holographic principle emerged from the study of black holes, where scientists noticed that the amount of information a black hole could contain was proportional to its surface area rather than its volume. This was a groundbreaking discovery that led researchers to consider the possibility that the entire universe could follow a similar pattern. Instead of viewing space and time as fundamental and unchanging components of reality, the holographic principle suggests that these dimensions might arise from a more basic and underlying structure that exists in a different realm, a lower dimensional reality, if you will. To grasp the implications of this, imagine watching a movie projected onto a screen. The images you see are not the film itself, but the result of light and information interacting with the surface of the screen. In a similar way, our three-dimensional experiences and even our perception of time could be the outcome of higher dimensional data being projected into the dimensions we experience. This idea suggests that our perceptions of space and life may not be the complete story. Instead, they could be mere reflections of a deeper, more fundamental layer of reality. If the holographic principle holds true, it invites us to reconsider not only the nature of space and time, but also our place in the cosmos. Are we truly perceiving the entire universe as it is, or are we merely witnessing a complex projection, an elaborate interpretation of a reality far more intricate and profound than we can imagine? This idea leads us to question the very nature of existence and reality, urging us to ponder whether everything we experience is simply a reflection of a deeper, unseen order. Catastrophic vacuum decay, another daunting concept in theoretical physics, adds yet another layer of complexity to our understanding of the universe. To understand this idea, we first need to consider what a vacuum means in the context of physics. A vacuum is not merely an empty space, but a state of lowest energy, one in which the potential energy is at its minimum. This type of vacuum is stable, allowing for the existence of particles and forces as we know them. However, there's a chilling possibility that our universe might occupy a false vacuum state, an unstable version of the true vacuum, which represents the lowest possible energy state. Imagine this scenario as sitting on top of a hill where the summit feels secure, but in reality, it's not the highest point. The true vacuum, in contrast, represents the bottom of a valley, stable and lower in energy. If our universe were to suddenly shift from this false vacuum to the true vacuum, the transition would be catastrophic. It would be like a marble rolling down the hill, suddenly and irreversibly plunging into a much lower position. Such a transition would not occur in a localized area, but instead it would ripple through space at the speed of light, transforming everything in its path into this lower energy state. The laws of physics as we know them could cease to exist, leading to an immediate and complete alteration of the universe as we understand it. This concept raises profound and unsettling questions about the stability of our universe. While the odds of such an event occurring are astronomically low, the possibility that we exist on the precipice of such a dramatic shift underscores the delicate balance that governs our reality. Each moment of existence relies on the intricate relationships between forces and particles, all within this seemingly stable vacuum state. Yet, as we go about our daily lives, the notion that something as monumental as vacuum decay could lurk just beyond our current reality compels us to reconsider how fragile our existence truly is, and how little we might actually understand about the cosmos. Parallel universes, another mind-bending concept, suggests the existence of many realities existing side by side with our own. Each of these universes represents a different variation, an alternate outcome of the universe we inhabit. To visualize this, imagine our universe as a vast tree, with each branch representing a different outcome, a distinct universe shaped by divergent events or choices made along the timeline. In this model, there could be an infinite number of branches, each representing a different version of reality, where every possible outcome plays out in its own universe. Scientists explore this idea through various theories, one of the most famous being quantum mechanics. This branch of physics delves into the strange and often unpredictable behavior of particles at the smallest scales. When a particle is observed, it appears to choose a specific outcome from a range of possibilities, much like the flip of a coin landing on one side or the other. This behavior leads some theorists to propose that every potential outcome of an event might correspond to a different universe, each one playing out its own version of the story, with every possibility manifesting in its own separate reality. In this multiverse model, the universe we experience is just one of many, each one a branch of possibility extending outward from the initial conditions of the cosmos. This raises intriguing questions about the nature of choice, that's chance, and fate. Is every action we take mirrored in a parallel universe where another version of ourselves experiences the alternate outcome? Or do the countless universes exist in a way that allows every possible future to unfold, creating an infinite number of variations, each as real as the one we inhabit? The idea of parallel universes, along with concepts like tachyons, the holographic principle, and vacuum decay, forces us to confront our deepest philosophical and scientific questions. What is reality? How do time, space, and matter interrelate? And perhaps most profound of all, are we truly alone in our understanding of the universe, or are there infinite versions of reality waiting to be discovered? However, some interpretations of the universe's mechanics propose a fascinating idea that all possible outcomes of any given decision or event actually occur, each in its own separate universe. In this scenario, when we make a choice or take an action, one version of reality unfolds, while countless other possibilities branch off into alternate realities, each one existing independently of the others. This theory is grounded in the notion that reality doesn't collapse into one singular linear outcome. Instead, it expands, creating an ever-growing web of universes, each operating under its own set of conditions, choices, and consequences. The sheer scale of these parallel worlds is mind-boggling, as each decision, from the smallest to the most monumental, spawns a new universe in which the alternate choice was made. In another approach to understanding the fabric of our existence, we turn to the concept of cosmic inflation. This theory, which builds on our understanding of the Big Bang, suggests that after the universe initially expanded, it underwent an extraordinarily rapid phase of inflation, expanding at a rate far beyond what we can currently comprehend. During this phase, pockets of energy began to form, each one giving rise to what could be seen as separate bubbles. These bubbles, each distinct from the others, continued to cool and evolve, eventually giving birth to their own unique universes. This concept suggests that the universe we inhabit may not be the only one. Far from it. These so-called bubble universes could have entirely different physical laws or constants, leading to realities that may look nothing like our own. They could, for instance, feature completely different forms of matter, entirely foreign forms of life, or even entirely alien structures of space-time itself. Though the existence of parallel universes remains speculative, the idea continues to captivate the imagination of scientists and lay people alike. We are currently unable to gather direct evidence of these alternate realities, making it both an enticing theory and a perplexing scientific frontier. While many scientists agree on the plausibility of a multiverse, a vast collection of universes coexisting alongside one another, our current technological limitations prevent us from observing or testing these dimensions. As a result, the multiverse remains a tantalizing puzzle, one that pushes the very boundaries of our understanding of existence itself. Hot Jupiters, a class of exoplanets that bear striking resemblance to our own Jupiter in terms of size and composition, provide another fascinating glimpse into the complexities of planetary systems beyond our solar system. These massive gas giants, however, do not orbit at the great distances we associate with Jupiter. Instead, they orbit exceptionally close to their stars, often in orbits much smaller than that of Mercury around our Sun. This proximity results in incredibly high temperatures that can soar to levels far beyond those found on Jupiter, earning them the moniker Hot Jupiter. Their immense size and proximity to their stars place them at the forefront of many astronomical investigations. The intriguing aspect of hot Jupiters lies not only in their size and orbital behavior, but in the unique atmospheric conditions they experience due to their extreme temperatures. The proximity to their parent stars means that these planets are bombarded by intense stellar radiation. This intense exposure can heat their atmospheres to staggering degrees, ranging from hundreds to even thousands of degrees Celsius. As a result, hot Jupiters often have thick, puffy atmospheres, which are capable of reflecting significant amounts of light and heat. These atmospheric features, combined with the complex mix of gases and thermal dynamics, make hot Jupiters an important subject of study. They offer insights not only into the planets themselves, but also into the broader dynamics of planetary formation and evolution. In addition to the extreme temperatures, hot Jupiters likely experience tumultuous weather patterns. The vast temperature differences between their day and night sides could create powerful winds and extreme storms. These gas giants may have weather systems that challenge our current understanding of atmospheric science, Gases that would typically exist as solids or liquids under the conditions of Earth could exist in entirely different states, contributing to dynamic and unpredictable weather systems. Such phenomena provide vital clues into how planets with extreme environments might evolve and adapt. As we study these weather systems, we expand our knowledge of how the universe behaves at its extremes and how life could possibly emerge in such harsh conditions. Hot Jupiters also challenge traditional models of planetary formation and migration. These planets, despite their size, seem to have defied the expectations of many scientists by forming far from their stars and then migrating inward over time. Instead of forming in the distant, colder regions of their stellar systems and slowly migrating inward, as was traditionally thought to be the case for gas giants, hot Jupiters have shown that planetary systems are more complex than we previously imagined. By studying these celestial bodies, astronomers are refining their models of planetary formation and migration, which could offer deeper insights into the diversity of environments in the universe. Super-Earths are another class of planets that hold the potential to reshape our understanding of habitability beyond Earth. These rocky planets, larger than Earth but smaller than the gas giants, are often found in diverse environments, particularly in the habitable zone of their stars, where liquid water could theoretically exist, a key ingredient for life as we know it. This placement within the habitable zone makes super-Earths especially intriguing to scientists, as water is one of the essential building blocks for biological processes. The study of these planets could reveal much about the conditions necessary for life to thrive beyond our own planet. The composition of super-Earths is also a critical factor in determining their habitability. Many of these planets possess thick atmospheres, often rich in gases such as carbon dioxide, which could play an essential role in supporting life. As scientists study the light emitted or reflected by these planets, they can analyze the chemical signatures of their atmospheres, looking for signs that indicate the presence of the building blocks of life. This process, known as spectroscopy, could eventually reveal whether these planets harbor conditions conducive to life, and perhaps even signs of life itself. In addition to their potential for harboring life, super-Earths often exhibit significant geological activity. This activity could play a key role in sustaining habitable conditions. Volcanoes and tectonic movement could recycle carbon and other essential nutrients, maintaining the balance necessary for life. The geological features of these planets could also help create diverse ecosystems, contributing to a robust biological environment. The study of such features offers a tantalizing glimpse into how life might flourish on other worlds. The possibility of diverse ecosystems, much like those on Earth, may not be so far-fetched after all. Some super-Earths also display seasonal changes in weather patterns similar to the Earth's own climate. Due to their tilted axes, these planets could experience varying seasons, which might create a wide range of ecological niches. Such variability could allow for the emergence of diverse life forms depending on the environmental conditions. This further opens the door to the possibility that life beyond Earth might not just exist, but could be thriving in forms very different from what we know. As our search for extraterrestrial life continues, the study of super-Earths provides a crucial opportunity to expand our understanding of where life could potentially exist beyond our solar system. Every discovery in this field takes us one step closer to answering one of humanity's most profound questions. Are we truly alone in the universe? Each new insight not only helps us understand the possibility of life beyond Earth, but it also helps us define what life itself might look like on other worlds. Venus, often called Earth's twin, provides a stark contrast to our planet in terms of both its size and composition. Despite its similarities in terms of mass and density, Venus is one of the most hostile environments in the solar system, making it an object of both intrigue and caution for scientists. The primary factor contributing to this extreme climate is the planet's thick atmosphere, which is largely composed of carbon dioxide, a greenhouse gas that traps heat to an extraordinary degree. This dense atmosphere is further thickened by clouds filled with sulfuric acid, creating an almost impenetrable layer around the planet. The effect of this atmosphere is nothing short of catastrophic for the surface conditions on Venus. The planet experiences a relentless greenhouse effect, trapping heat and raising the surface temperature to such extremes that it can melt lead. These high temperatures make Venus an inhospitable place for life as we know it, and any spacecraft attempting to land on the surface of Venus is quickly overwhelmed by the searing heat and corrosive atmosphere. Despite these challenges, the study of Venus continues to provide critical insights into atmospheric science, climate dynamics, and the processes that can make a planet either habitable or deadly. Through the study of both extreme environments like Venus and the potential habitability of super-Earths, hot Jupiters, and parallel universes, humanity's quest to understand the nature of existence expands into increasingly uncharted territories. The more we learn, the closer we come to comprehending not just our place in the cosmos, but the immense diversity of possible worlds that could exist within the vast expanse of the multiverse. The atmospheric pressure on Venus is an extreme force to reckon with. It is about 90 times greater than the pressure we experience here on Earth, equivalent to being nearly a mile beneath the ocean's surface. This immense pressure would easily crush any spacecraft brave enough to attempt a landing without specially designed engineering capable of withstanding such hostile conditions. Venus is not a place where human exploration can occur without massive technological innovation, and even then, the odds seem insurmountable. The winds on Venus add yet another layer of danger, reaching speeds that can surpass 200 miles per hour. These violent winds whip through the upper atmosphere, creating turbulent weather patterns that are not just hazardous, but also unpredictable. Above the surface, the thick clouds, although high up, play a crucial role in shaping the planet's environment. They form a perpetual shroud that reflects much of the sunlight that strikes Venus. As a result, Venus is incredibly bright when viewed from space, but that same cloud cover prevents any cooling effect from the day-night cycle that we rely on here on Earth. Despite the planet's proximity to the sun, Venus does not experience temperature fluctuations the way we do. The clouds trap heat, preventing any natural cooling, and the constant volcanic activity on the surface suggests that the planet continues to release heat from within. This creates an atmosphere that remains consistently hot, so much so that surface temperatures are capable of melting lead. With temperatures that stay this high, crushing atmospheric pressures, acidic clouds, and relentless winds, Venus presents an environment so extreme that survival as we know it would be nearly impossible. In many ways, the harshness of Venus's environment serves as a powerful reminder of just how diverse planetary conditions can be within our own solar system. A few thousand miles away, Venus's inhospitable surface stands in stark contrast to the serene, life-supporting environment that we have on Earth. Turning to the Moon, one of the more captivating areas of scientific intrigue has always been the so-called dark side. For decades, scientists have been fascinated by this mysterious hemisphere, mainly because it remains shrouded in secrecy. It is the side of the Moon that faces away from Earth, hidden from view due to the Moon's synchronous rotation, the phenomenon where the Moon takes the same time to spin on its axis as it does to orbit our planet. Contrary to what the name suggests, the dark side of the Moon isn't perpetually dark. It receives the same amount of sunlight as the side we can see. It simply does not face Earth. This hidden hemisphere has sparked intense curiosity, primarily due to its geological features and unexplored environments. From deep craters to ancient lunar maria, the surface offers clues to the Moon's history and, by extension, the broader history of our solar system. Some scientists speculate that studying this side could offer valuable insights into the processes that shape not only the Moon but also Earth and other celestial bodies in our cosmic neighborhood. By understanding these processes, we can unlock a deeper comprehension of the early solar system and the forces that led to the formation of the planets and their moons. Beyond its geological intrigue, the dark side of the Moon offers another unique opportunity for scientific advancement: radio astronomy. Unlike the visible side of the Moon, which is affected by Earth's radio emissions, the far side provides a pristine environment free from interference. This quiet region allows for the capture of faint signals from deep space, which could lead to breakthroughs in our understanding of the early universe. Studying these signals might reveal how galaxies, stars, and even the fundamental properties of space itself came into being. The challenges of exploring the dark side of the moon have also pushed the boundaries of space exploration, requiring innovations in communication, navigation, and mission planning. As spacecraft venture into this uncharted territory, they promise to expand our understanding not just of lunar science, but of the entire cosmos. The mission to explore the far side of the moon exemplifies how sometimes the most groundbreaking discoveries lie beyond our current view, waiting to be uncovered. Jupiter, the gas giant that reigns supreme in the outer reaches of our solar system, holds within its atmosphere a storm that has captivated scientists for centuries, the Great Red Spot. This colossal storm is not just remarkable for its size, but also for its longevity, making it one of the most enduring weather systems we've ever observed. The Great Red Spot is a massive anticyclonic storm, which means it rotates in the opposite direction of the storms we typically see here on Earth. To put its scale in perspective, imagine a hurricane several times the diameter of our planet, swirling endlessly in Jupiter's upper atmosphere. The dynamics that drive storms like the Great Red Spot are rooted in the unique atmospheric conditions of gas giants. Jupiter's atmosphere is primarily composed of hydrogen and helium, and its immense size and rapid rotation generate extreme thermal dynamics. These conditions create powerful wind currents and convection cells that fuel the continuous formation of storms. The Great Red Spot's persistence can be attributed to several factors. The immense energy within Jupiter's atmosphere is capable of sustaining the storm, and its vast scale means even a small amount of energy can keep it going for centuries. Unlike storms on Earth, which can dissipate when they move over land or encounter cooler temperatures, storms on Jupiter can endure because they are surrounded by vast regions of gaseous material that allow them to thrive. The constant rotation and the continuous input of energy from Jupiter's interior combine to maintain the Great Red Spot, making it a truly awe-inspiring feature in our solar system. Despite the complexity of the forces at play, one thing remains clear. The storm will likely continue to rage, a testament to the immense power of Jupiter's atmosphere and the vastness of the forces that govern our solar system. In the end, these extreme environments, Venus with its crushing pressures and scorching temperatures, the moon's hidden hemisphere full of mysteries, and Jupiter's unyielding Great Red Spot remind us of just how vast, varied, and awe-inspiring our solar system truly is. They are stark reminders that, in the grand scheme of things, Earth's temperate climate and conditions that support life are but one tiny part of a much larger cosmic picture. These planetary extremes serve as both challenges to human exploration and inspirations for our boundless curiosity. Moreover, these intense storms are perpetuated by the very forces that sustain their existence. As they swirl and spin, the storms create boundaries within their own structure, which act as stabilizers, preventing them from collapsing under their own immense power. The dynamic interplay between these forces, wind patterns, temperature fluctuations, and the intricate interactions with other atmospheric systems, plays a crucial role in maintaining their stability. This synergy between the storm's inner workings and its outer environment helps preserve their form and intensity for an astonishingly long time. One of the most striking examples of this phenomenon is Jupiter's Great Red Spot, a storm that has been raging for centuries. The persistence of such storms is not a coincidence, but rather the result of the planet's unique atmospheric conditions. The immense energy constantly being fed into the storm, combined with Jupiter's thick, turbulent atmosphere, creates a perfect environment for storms to thrive. This combination of factors ensures that the storm remains active and continues to exist for such a long period. The swirling gases that compose Jupiter's atmosphere interact with one another in complex patterns, constantly fueling and maintaining the storm. The result is an awe-inspiring spectacle that has captivated scientists, astronomers, and stargazers alike for generations. It serves as a reminder of the immense forces at play within the gas giant's weather systems, forces that are both grand in scale and incredibly intricate in their execution. In a similarly captivating, yet entirely different realm, cryovolcanoes, also known as ice volcanoes, present an entirely new concept of volcanism. These fascinating geological features are found on icy moons and certain planets, where eruptions do not consist of molten rock, but rather frozen or semi-frozen substances. Cryovolcanoes eject a mixture of water, ammonia, or methane, which, instead of flowing like lava, behaves like a slow-moving river of ice. This unique form of volcanism provides scientists with crucial insights into the subsurface processes of these icy bodies. The driving force behind these eruptions lies deep within the celestial bodies, where internal pressures build over time. These pressures arise from heat generated by radioactive decay or from tidal forces caused by gravitational interactions with a parent planet. As these forces accumulate, they create enough pressure to expel a volatile mixture of ice and chemicals from below the surface. This release results in cryovolcanic activity, reshaping the surface and forming features that resemble traditional volcanoes, but with an entirely different texture. Smooth domes or sharp ridges created by the frozen eruptions. What makes cryovolcanism so intriguing is that it suggests much more than just a frozen exterior. The presence of these ice volcanoes hints at a dynamic interior, one that may harbor a liquid layer beneath the ice. This discovery is key to understanding the potential for life in these cold, distant worlds. For instance, moons like Enceladus and Europa, which are covered by thick ice sheets, have shown signs of cryovolcanic activity, pointing to the possibility of subsurface oceans. If these moons indeed harbor liquid water beneath their icy crusts, they could provide the right conditions for life to exist. By studying these ice eruptions, scientists can gather invaluable information about the history, geology, and evolution of these celestial bodies. The composition of the materials expelled during cryovolcanic eruptions offers clues about the moon or planet's internal structure, past climate conditions, and the geological processes that have shaped their surfaces over time. Cryovolcanoes not only provide a glimpse into the dynamic forces shaping the outermost layers of these moons, but they also serve as windows into the complexities of life in the far reaches of our solar system. In the most extreme environments on Earth, a fascinating group of organisms called extremophiles manage to thrive where life once seemed impossible. These organisms can survive in conditions that would obliterate most forms of life. Some extremophiles live in the boiling waters of hot springs where temperatures soar to levels that would scald anything else. Others thrive in the crushing depths of the ocean, where pressures are so intense that few creatures could withstand them. Still others manage to survive the harsh radiation found on the surface of other planets. These remarkable organisms challenge our understanding of life itself, proving that life can adapt to survive in environments that would be considered inhospitable by conventional standards. From extreme temperatures and high acidity to high salinity and complete darkness, extremophiles show that life is far more resilient than previously thought. Their existence has opened up exciting new possibilities for the search for extraterrestrial life. If life can survive and even thrive in such extreme conditions on Earth, it stands to reason that similar life forms might exist in the harsh environments of other worlds. Take, for example, the moons of Jupiter and Saturn, Europa and Enceladus. These moons are encased in thick layers of ice, yet beneath their frozen surfaces lies vast hidden oceans of liquid water. Despite the frigid temperatures and the absence of sunlight, these moons could very well harbor extremophilic life forms. These organisms, if they exist, would likely derive their energy from chemical reactions rather than sunlight, much like some of the extremophiles found in the deepest, most isolated corners of Earth's oceans. The discovery of extremophiles has profound implications for our understanding of where life might be found beyond Earth. It has shifted the focus of the search for extraterrestrial life from just looking for habitable planets with Earth-like conditions to considering a far wider range of possibilities. Moons, comets, and even planets with icy exteriors and active surfaces are now prime targets for exploration, as they may hold the key to answering one of humanity's oldest questions. Are we alone in the universe? Moreover, the study of these extraordinary organisms, known as extremophiles, plays a pivotal role in helping researchers unravel the types of life that could potentially evolve in extraterrestrial environments. By understanding how these hardy life forms metabolize and reproduce in extreme conditions, scientists gain invaluable insights into the biological processes that might take place elsewhere in the universe. In many ways, extremophiles expand the very definition of life, pushing the boundaries of what we once thought was possible. They inspire and encourage scientists to venture into the farthest reaches of space, exploring places like Mars, where the soil is acidic and radiation is prevalent, or the hidden subsurface oceans of distant moons, which may harbor life in ways we have yet to comprehend. Extremophiles are nature's pioneers, demonstrating resilience and adaptability in the face of seemingly insurmountable adversity. These organisms remind us that life has an uncanny ability to find a way to thrive even under the most hostile of conditions. Their existence serves as a powerful testament to the resilience of life and encourages us to continue the search for signs of life in the most unexpected corners of the cosmos. As researchers deepen their exploration into these organisms, they are increasingly convinced that life in one form or another could survive in environments previously thought to be far too extreme for biological activity. In the grand scheme of things, Saturn's rings are one of the most breathtaking features of our solar system, captivating both scientists and space enthusiasts alike. These iconic rings are made up of countless tiny particles, primarily composed of ice and rock, each one orbiting the planet at varying distances. What makes Saturn's rings truly unique is their composition and structure. They span a vast distance from the planet, stretching thousands of kilometers wide, yet are incredibly thin. Some parts are only about 10 meters deep. This dramatic difference in scale demonstrates the complex dynamics within the ring system, where gravitational forces, particle interactions, and other physical processes come into play. The vibrant colors and distinct patterns of Saturn's rings are a result of the varying sizes and compositions of the particles within them. Larger chunks of ice reflect light differently than smaller grains, creating a beautiful and ever-changing canvas that shifts depending on the angle of sunlight and the observer's position. These rings are not just a random collection of particles, they are an intricate system governed by powerful gravitational interactions. The moons of Saturn play a major role in shaping these rings through their gravitational influence. Known as moonlets, these moons interact with the particles in the rings, trapping some while pushing others away, contributing to the creation of gaps and distinct patterns within the ring system. Yet the mysteries of Saturn's rings extend far beyond their stunning appearance. One of the most captivating questions scientists face revolves around the age of these rings. Some researchers propose that Saturn's rings may have existed for millions of years, while others suggest they could be much younger, possibly formed by the remnants of a moon that was torn apart by Saturn's immense gravitational forces. This has led to an ongoing debate about the longevity of such a structure and what their existence can tell us about the evolution of planetary systems. As scientists continue to study Saturn's rings, they hope to unlock even more secrets about their origins and the processes that govern them. One particularly fascinating aspect of Saturn's rings is their interaction with Saturn's magnetic field. This interaction often leads to the formation of waves and ripples within the rings, hinting at the dynamic, complex processes that occur in this cosmic environment. Moreover, the gravitational pull of Saturn does more than simply influence the shape of the rings. It may also provide critical clues about the planet's own formation and history. As researchers continue their studies, Saturn's rings remain a remarkable and enigmatic window into the processes that shape not only planetary systems, but also the evolution of gas giants like Saturn itself. In the broader scope of space exploration, the quest to study exoplanets, planets that exist outside our solar system, has taken us on an extraordinary journey. Every discovery reshapes our understanding of the cosmos, challenging long-held assumptions about how planets form and how they coexist with their stars. For much of history, scientists believed that solar systems like our own were the standard. However, the search for exoplanets has revealed an astounding diversity of planetary systems. Some exoplanets host gas giants that orbit extremely close to their stars, while others are rocky worlds located in unexpected places. This vast diversity raises profound questions about the conditions necessary for a planet to support life. While Earth-like conditions once seemed to be unique in the universe, we now realize that the potential for life could extend to environments previously thought inhospitable. Some exoplanets, for instance, might reside within their star's habitable zone, the region where conditions are just right for liquid water, which is considered essential for life as we know it. Yet, other exoplanets might thrive in environments defined by extreme conditions, thereby challenging our existing definitions of what constitutes a viable habitat. The techniques used to discover these far-off worlds have added layers of complexity to our understanding. Methods such as transit photometry and radial velocity measurements offer a wealth of data, allowing scientists to study the atmospheres of distant exoplanets. By analyzing the chemical compositions of these distant worlds, researchers can identify potential markers for life or uncover hints of unique geological processes. As more data is gathered and analyzed, it becomes clear that many of the models we once used to understand planetary formation and evolution must be reconsidered. With each new exoplanet discovered, scientists must refine their theories and expand their imaginations to account for the vast variety of planetary systems that populate our universe. With advancing technology, the search for exoplanets promises to deepen our understanding of the cosmos. This journey may eventually redefine our place in the universe, opening up new possibilities and shifting our perspective on the conditions necessary for life. As we continue to uncover new worlds, the potential for discovering life, either in forms similar to what we know or something entirely unique, becomes ever more likely. The theory of relativity, introduced by Albert Einstein, has profoundly reshaped our understanding of time and space. It has challenged long-held assumptions about the very fabric of reality. Before Einstein's theory, time was often imagined as a constant, an unchanging clock that ticked uniformly for everyone, everywhere. Similarly, space was thought of as a stage where events unfolded in a consistent, predictable manner. However, relativity shattered these concepts, revealing that time and space are far more fluid and interconnected than we could have ever imagined. Time no longer flows the same for everyone, and space itself can warp and bend under the influence of gravity, forever altering our view of the universe. Through this revolutionary theory, scientists have come to realize that the very nature of reality is far more complex than we once believed, forcing us to confront new questions about the universe and our place within it. As we continue to delve deeper into the implications of relativity, we move ever closer to unlocking the mysteries of time, space, and the cosmos itself. However, relativity introduces a profound shift in how we perceive the nature of time and space. It invites us to reconsider the very fabric of reality itself, offering a more fluid and dynamic understanding of existence. According to this theory, time is not a fixed, universal experience, but instead varies based on an observer's speed and the gravitational field in which they find themselves. This insight leads to an intriguing realization. Two observers experiencing the same physical events might perceive time in completely different ways depending on their relative motion. The implications of this idea are both revolutionary and deeply philosophical. If time is not the same for everyone, what does that mean for our understanding of reality? It challenges the notion of a singular, absolute present moment, one that all of us share. Instead, it suggests that each observer exists within their own unique temporal framework, shaped by their velocity and the gravitational forces acting upon them. In this way, the passage of time becomes inherently subjective. Our memories, experiences, and even our understanding of the world could be entirely shaped by our individual perspective of time. When we expand this notion into the realm of space, relativity presents an equally surprising idea. Distances are not fixed measurements, but can expand or contract depending on the relative motion and the influence of gravity. This revelation transforms our understanding of the universe from a rigid, unchanging container into a fluid, dynamic arena. The space between two objects is not static, but rather stretches or shrinks as the objects themselves move through space and time. This realization forces us to reconsider our own place in the universe. The position we occupy, both physically and temporally, shapes our perception of reality. At the core of relativity is a series of profound philosophical questions about existence itself. If time and space are relative, what does this imply about our lives, histories, and identities? Are our experiences, memories, and very selves intrinsically tied to our specific frames of reference? The shift in perspective encouraged by relativity challenges us to rethink our fundamental assumptions about what it means to be alive and to exist. It calls for a more interconnected view of life, one in which our individual realities shaped by the broader dynamics of the cosmos are more alike than we may have initially believed. The philosophical legacy of relativity compels us to re-examine our concepts of truth, experience, and the nature of reality. In many ways, it pushes us toward a deeper understanding of the universe and our place within it, urging us to confront the question, if time and space are not absolute, what does it mean to be truly real? One of the most captivating aspects of relativity is the concept of time dilation, which offers a radically different perspective on how we experience reality. Time dilation suggests that time passes at different rates depending on the circumstances an observer finds themselves in. To better understand this, imagine two observers, one moving rapidly through space and the other at rest. For the observer who remains stationary, time proceeds normally, ticking away as seconds, minutes, and hours pass. But for the traveler in motion, time slows down relative to the stationary observer. As the speed of the traveler increases, approaching the speed of light, the effects of time dilation become even more pronounced. What might feel like only a brief journey for the traveler could, in the eyes of an observer at rest, stretch across years, decades, or even centuries. This concept radically alters our understanding of time as a fixed, linear process. Instead, it reveals that time is a flexible, subjective experience influenced by the observer's velocity and the gravitational environment they are in. The consequences of time dilation stretch far beyond the realm of physics. If we consider aging as a marker of time's passage, then the traveler who experiences time dilation may return from their journey significantly younger than their peers who remained behind. This creates a paradox, one that not only challenges our ideas of physical experience, but also raises deep philosophical questions about identity, existence, and the very fabric of the universe. If time is relative, how does that affect our notions of personal experience and the unfolding of life itself? What does it mean to exist in a universe where time, the one constant we believed we could rely on, is no longer fixed? Time dilation reshapes our perception of reality, revealing that the passage of time is more subjective and malleable than we might have thought. It alters the way we think about the progression of our lives and our personal experiences across the cosmos. If time can bend and stretch depending on one's motion, how do we reconcile this with our everyday understanding of life as a linear sequence of events? How does this affect our notions of aging, relationships, and the very concept of the present? One of the most intriguing and perplexing consequences of thinking about time in this way is the idea of causality loops. These loops, which arise from a non-linear understanding of time, present a scenario where cause and effect are no longer straightforward. Imagine a situation where an event occurs that causes another event, but that second event, in turn, causes the first. In essence, time begins to loop back on itself, creating a circular flow of events that defy traditional cause and effect. In a world where time is no longer linear, causality loops suggest a reality where events might not unfold in a clear, progressive order. Take the example of a time traveler who returns to the past and inadvertently sets off a series of events that lead to their own existence. In this scenario, the time traveler both causes and is the effect of their own existence, leading to a paradox. They would not exist without having traveled back in time, but their travel through time is only possible because they already exist. In this way, time loops challenge our understanding of past, present, and future. Traditionally, we view time as a linear progression, moving from past to future. However, causality loops disrupt this simple flow, suggesting that events can form a tangled web where the sequence of events is not as clear-cut as we once assumed. This leads us to question the very foundations of reality itself. If events can be self-causing, what does that mean for free will, destiny, and our ability to influence the future? Can our actions create situations that have already happened? What does this imply about the structure of time and our understanding of causation? Causality loops push us to rethink the very nature of time, suggesting that it may not be the straightforward linear experience we take it to be. Instead, time may be a complex, interconnected web of events where cause and effect are not always easily separated. This understanding opens up new possibilities for exploring the universe, offering a far more intricate and mysterious view of how events unfold. The concept of the space-time continuum, a central tenet of modern physics, offers a further shift in our understanding of reality. Rather than thinking of space and time as separate, distinct entities, the space-time continuum posits that they are inextricably intertwined, forming a four-dimensional fabric. In this framework, every event in the universe occurs at a unique point in both space and time. You cannot separate the two. Every event has a specific when and where that define its place in the cosmos. In this view, massive objects like planets and stars warp this fabric, bending it in ways that we perceive as gravity. The presence of mass doesn't just influence the space around it, it also alters the flow of time. An object in a strong gravitational field experiences time more slowly than an object in a weaker field. This phenomenon has been confirmed by experiments such as those involving precise atomic clocks on satellites, which show that time runs slightly faster in space than on Earth due to the difference in gravity. This interconnectedness of space and time challenges our traditional understanding of the universe, suggesting that the very nature of reality is more fluid and dynamic than we ever imagined. As we continue to explore the implications of relativity, we begin to see a universe that is far more complex and interconnected than the simple, static reality we once believed in. The idea of the universe's vastness and its unfolding events invites us to look beyond our conventional understanding of reality. Imagine, if you will, a massive sheet stretching out infinitely in all directions. Now, place a heavy object on that sheet. As the object settles into its position, the sheet warps and bends under its weight. This simple visual is a striking analogy for how space-time behaves around large celestial bodies. The mass of planets, stars, and even black holes distorts the very fabric of space-time, altering the way that both time and space function in those regions. Such a fundamental shift in understanding opens doors to profound implications for cosmic phenomena. Black holes, for instance, are extreme examples of this warping, a point in space where the pull of gravity is so intense that not even light can escape. Similarly, the movement of objects across vast, seemingly infinite distances becomes comprehensible when viewed through the lens of space-time curvature. This continuum, as it is known, is not just a theoretical concept, but one that drives the groundbreaking theory of relativity, formulated by Albert Einstein. The theory fundamentally altered our understanding of how the universe operates, particularly in terms of motion and the speed of light. According to the theory of relativity, space and time are not static entities, but flexible, interconnected dimensions that react to the presence and movement of mass. This means that observers moving at different speeds will measure time and distance differently. An individual traveling at a speed close to the speed of light, for example, would experience time differently from someone at rest. This phenomenon, known as time dilation, is one of the most fascinating consequences of Einstein's insights. At velocities approaching the speed of light, time for the traveler slows down relative to someone who is stationary. The very passage of time itself becomes fluid, stretching and contracting based on the observer's motion. Through the intricate framework of the space-time continuum, we can begin to grasp the dynamic nature of our universe. Here, both spatial dimensions and the flow of time interact with one another, creating a cosmic stage where everything is in constant motion. This comprehensive view of the universe transforms how we comprehend reality, offering scientists new ways to approach complex questions about the origins of existence, the nature of time, and the forces that drive the cosmos. Our understanding of black holes, the behavior of light, and even the trajectory of distant planets are all shaped by this framework. As we venture deeper into the mysteries of the cosmos, a thought-provoking question arises. Does the universe have an edge? This idea challenges everything we know about space and existence. To entertain such a concept, we must first understand the nature of the universe itself. Modern cosmology suggests that the universe is continuously expanding, yet this expansion is not happening into an empty space with a defined boundary. Instead, the universe is often described as a three-dimensional structure that curves upon itself, creating a closed loop. In such a model, if you were to travel in any direction far enough, you would eventually find yourself back at the point where you began, much like a traveler circling the Earth. However, imagining the existence of an edge requires us to push the boundaries of our imagination. If such an edge were to exist, it might represent a place where the laws of physics as we know them start to break down. Approaching this boundary, the fabric of space itself could stretch endlessly, warping light and distorting our perception of reality. We could encounter a shimmering horizon, a point beyond which the very concept of space becomes unrecognizable. Extreme conditions would dominate this region, temperatures fluctuating unpredictably, gravitational forces pulling at the very fabric of matter, and the very nature of existence itself becoming increasingly unstable. Beyond this hypothetical edge, we might find an area where matter thins out to near non-existence, leaving behind vast stretches of emptiness. Time, too, could behave in entirely unpredictable ways. No longer flowing in a linear fashion, it might swell or contract in irregular patterns, challenging our understanding of past, present, and future. At this point, the very nature of time itself could become elusive, potentially ceasing to have the same meaning we attribute to it in our everyday lives. Despite these tantalizing possibilities, the notion of an edge remains speculative at best. Current cosmological theories suggest that the universe is not a static, finite entity with a clear boundary, but rather an evolving and expanding system, constantly unfolding in ways that are still not fully understood. The very idea of a definitive edge seems increasingly elusive as scientists continue to explore the mysteries of the universe. These efforts have led us to contemplate realms that extend beyond our observable reality, encouraging us to entertain possibilities that stretch the limits of human imagination. One particularly mind-bending idea that arises when considering such cosmic phenomena is the potential for time paradoxes. Such paradoxes would fundamentally challenge our understanding of causality, the principle that a cause precedes an effect. In our daily lives, events seem to unfold in a clear linear sequence. We make decisions that lead to consequences, and the future is shaped by the actions of the present. But in a universe where time can bend, stretch, and fold, the very foundation of cause and effect becomes questionable. If time can behave in such unpredictable ways, might we encounter situations where events unfold in reverse order, or where the future influences the past? These are questions that defy conventional logic and reveal just how much we have yet to learn about the true nature of the cosmos. As science continues to delve deeper into the enigma of space-time and its infinite complexities, we are reminded of the vast, unexplored frontiers that lie just beyond our current grasp, waiting to challenge everything we think we know about the universe. However, a time paradox introduces scenarios where the natural sequence of events becomes tangled, raising profound and complex questions about how we perceive reality itself. Imagine a situation where someone travels back in time only to inadvertently alter a critical historical event, perhaps even preventing their own existence. This sets in motion a paradoxical loop of impossibility. The very act of changing the past directly contradicts the existence of the time traveler in the first place. Such paradoxes reveal the fragile and perplexing nature of our understanding of time as they challenge our conventional views and force us to reconsider the foundational concepts of causality and existence. These temporal conundrums suggest that our traditional perception of time may be overly simplistic and inadequate to fully comprehend the infinite complexities of the universe. As scientists grapple with the implications of time paradoxes, they explore various theories that seek to accommodate the seemingly contradictory phenomena. One such theory involves the concept of multiverses, an idea that posits every decision or action branches off into an alternate reality, creating a multitude of possible timelines. In this framework, altering the past doesn't negate the original timeline. Rather, it spawns an entirely new path, a parallel reality that coexists alongside the original. This multiverse approach provides a more sophisticated and nuanced understanding of causality, one that embraces the possibility of multiple outcomes, each existing within its own separate universe. It challenges the idea of a linear, singular reality and opens up the potential for an infinite number of timelines, each influenced by the actions of individuals and the choices they make. The exploration of time paradoxes, therefore, pushes the boundaries of both physics and philosophy, compelling us to reconsider the very fabric of time and how we relate to it. It urges us to question the nature of free will, the intricacy of events, and the interconnectedness of all things. As we delve deeper into these mind-bending possibilities, our curiosity intensifies, and we are left with even more profound questions about the nature of existence, the interplay between choice and fate, and the ultimate structure of the universe itself. Could the concept of time itself be an illusion? What are the consequences of changing past events, and what do those consequences say about our place in the cosmos? The answers to these questions remain elusive, but the exploration of time paradoxes opens up new pathways of thought, offering a glimpse into a reality far more intricate and mysterious than we could have ever imagined. Similarly, the history of human space exploration serves as a remarkable chronicle of our unyielding curiosity and ambition to understand the universe. Our journey beyond Earth began in the mid-20th century, marked by the historic launch of Sputnik, the first artificial satellite, by the Soviet Union in 1957. This monumental event not only signified humanity's first foray into space, but it also ignited a fierce competition among nations to dominate the new frontier, sparking a technological revolution that would change the world forever. In the years that followed, humanity's aspirations soared higher, culminating in the achievement of one of the most iconic milestones in human history, the successful landing of humans on the moon in 1969. This was no mere scientific achievement. It was a moment of unity, a collective triumph for all of humanity that showcased our boundless potential to transcend the boundaries of Earth and venture into the cosmos. The Apollo program, led by NASA, brought together engineers, scientists, and visionaries to make the impossible possible, and their success continues to inspire generations. Following the triumph of Apollo, space exploration expanded beyond the moon with the advent of space stations such as the Soviet Mir and later the International Space Station, ISS. These orbiting laboratories transformed our understanding of life in space, offering invaluable insights into the effects of microgravity on the human body and advancing international collaboration in scientific research. The ISS, in particular, has become a symbol of global cooperation, with astronauts from various nations working side by side to unravel the mysteries of space and improve life on Earth. Meanwhile, unmanned missions to distant planets and moons further broadened our horizons. Probes like Voyager, which have journeyed into the far reaches of our solar system, carry humanity's stories and discoveries to the edge of the cosmos. These robotic explorers have unlocked secrets of distant worlds, uncovering phenomena that were once the stuff of science fiction. The Mars rovers, along with missions to the outer planets like Jupiter and Saturn, have provided invaluable insights into the potential for life beyond Earth and the origins of our solar system. With every discovery, our understanding of the universe deepens, and we are reminded of how much we have yet to learn. Each step in the journey of space exploration has reshaped our understanding of our place in the cosmos. As we send machines to distant worlds, we are forced to confront the intricate and delicate dynamics of our own planet. The more we discover about the universe, the more we recognize the fragility of Earth's environment and the interconnectedness of all life. From the search for water on Mars to the identification of exoplanets orbiting distant stars, our exploration of space has fueled a renewed sense of wonder and a shared commitment to safeguarding the home we have on this small, beautiful planet. Indeed, the history of space exploration is a testament to humanity's relentless pursuit of knowledge. It challenges us to rethink our understanding of existence, pushing us to ask profound questions about life beyond Earth and the future of our species. With each new discovery, we are reminded that we are part of a much larger cosmic tapestry, one that connects us to the stars and urges us to cherish and protect the fragile world we inhabit. In the quest to understand the cosmos, astronomers employ a variety of techniques to measure the geometry of space, offering critical insights into the universe's structure and limits. One of the most fundamental methods involves observing the light emitted by distant celestial objects by analyzing the way light stretches or shifts, a phenomenon known as redshift. Astronomers can determine how fast an object is receding from us. This redshift occurs because the universe is expanding, and the farther away a galaxy is, the faster it appears to be moving away from us. This observation provides an essential sense of the vastness of the cosmos and offers clues about its overall shape and destiny. Another key technique is parallax, or geometric triangulation, which involves measuring the position of a star from two different points in Earth's orbit around the Sun. By comparing these measurements, astronomers can calculate the distance to the star with remarkable accuracy. These distance measurements serve as the foundation for mapping the cosmos in 3 dimensions, helping scientists create a more detailed and accurate model of the universe's structure. Beyond these methods, astronomers also study the cosmic microwave background radiation, CMB, which represents the afterglow of the Big Bang. This faint, omnipresent radiation fills the universe and provides a snapshot of the early cosmos, offering clues about its age, composition, and structure. By analyzing the temperature variations and density fluctuations in the CMB, astronomers can infer whether the universe is flat, open, or closed, offering crucial insights into the universe's geometry on the largest scales. These techniques collectively allow us to probe the deepest mysteries of the universe, uncovering new layers of understanding and pushing the boundaries of what we know about the cosmos. Astronomers today have access to a range of groundbreaking technologies, allowing them to study the universe with a level of detail and precision that was once unimaginable. One such technique that has revolutionized our understanding of the cosmos is gravitational lensing. In essence, this phenomenon occurs when the gravity of a massive object, such as a galaxy or even a cluster of galaxies, bends and distorts the light from objects located behind it. This bending of light creates magnified, warped, or even multiple images of distant celestial bodies, acting as a natural magnifying lens. By analyzing these distortions, scientists can estimate the mass of the foreground object responsible for the lensing and, in turn, make inferences about the distribution of matter in the universe. Gravitational lensing is just one of many methods that astronomers use to study the vast and often mysterious expanse of space. Combined with other observations, these techniques offer a more comprehensive understanding of the geometry of the universe. With each new discovery, astronomers are able to piece together a clearer picture of the universe's structure, its origins, and its evolution. As more data is gathered, new theories about the fate of the universe continue to emerge. Will it expand forever, gradually growing colder and more distant, or will it eventually collapse under its own gravitational pull, leading to a big crunch? Alternatively, could it maintain a steady state, remaining unchanged for eternity? These questions, once speculative, are becoming the focus of ongoing research, drawing both scientists and the general public into an awe-inspiring exploration of the cosmos. Every new finding captivates our imaginations, deepens our understanding of space, and ultimately brings us closer to grasping the true nature of the universe we inhabit. However, understanding the true nature of time remains an elusive challenge for scientists. At its core, time is used as a measure to track the duration and order of events. Yet what time actually is continues to spark intense debate across multiple disciplines, from physics to philosophy. One of the greatest challenges in conceptualizing time is its intrinsic connection to the physical reality of the universe. The complexity of time is revealed through Einstein's theory of relativity, which shows that time is not a constant, unchanging entity. Rather, it is relative. Its passage depends on both the speed at which an observer is moving and the strength of the gravitational fields surrounding them. This concept introduces a fascinating twist. Two observers in different locations or moving at different speeds may experience different durations for the same event. This relativity of time complicates the search for a singular definition of time that can apply universally. It suggests that Time, rather than being a fixed backdrop against which events unfold, is an adaptable, fluid dimension that shifts based on perspective. Time is not a simple, linear concept. It bends and twists, influenced by the very fabric of space itself. This brings us to another layer of difficulty: the relationship between time and space. In modern physics, time and space are not considered separate entities, but rather interwoven into a single, four-dimensional construct known as space-time. This connection complicates our ability to isolate time as a standalone concept. Events, both in the present and across the cosmos, are defined within this framework, which makes it incredibly challenging to study time independently of space. Scientists attempting to break down the components of space-time encounter profound difficulties in trying to understand how time is influenced by the spatial dimensions that surround it. The origin of time itself remains a profound mystery. Questions persist about what happened before the universe began. Did time even exist in the same form prior to the Big Bang, or did it emerge alongside the universe? These questions are not merely academic. They reach into the very foundations of cosmology. Understanding the beginning of time is essential for understanding the nature of existence itself. Without answers to these questions, our grasp of time will always remain incomplete, leaving room for further exploration and discovery. Philosophically, the nature of time raises deep and fundamental questions. Is time something that flows continuously, or is it merely a human construct, a tool designed to organize our experiences and understand the world around us? This distinction has profound implications for the direction of scientific endeavors, particularly when it comes to reconciling seemingly incompatible theories in physics. For instance, merging quantum mechanics, the study of the very small, and general relativity, the theory that governs the behavior of massive objects, remains one of the biggest challenges in modern science. Time plays a central role in these efforts, and understanding its true nature is essential to bridging the gap between the two theories. Ultimately, unraveling the mysteries of time involves a multi-layered journey through physics, mathematics, and philosophy. Each new discovery raises even more questions, keeping scientists and thinkers engaged in an ongoing dialogue about this elusive dimension. The quest to understand time is far from over, and with each breakthrough, we move one step closer to understanding one of the most fundamental aspects of the universe. In the vast, turbulent depths of space, another cosmic phenomenon poses a significant potential threat to life on Earth: gamma-ray bursts. These incredibly energetic explosions are among the most powerful events in the universe, unleashing a staggering amount of energy in a fraction of a second. To put this in perspective, a single gamma-ray burst can emit more radiation in just a few seconds than the sun will release throughout its entire lifetime. Though they occur far away from Earth, should such an event happen within a few thousand light years, the effects could be catastrophic for life on our planet. The primary concern with gamma-ray bursts lies in their intense gamma radiation, which can have devastating consequences. If a gamma-ray burst were to occur nearby, the radiation could strip away much of Earth's protective atmosphere, including the ozone layer, which serves as a vital shield against harmful ultraviolet radiation. This depletion of the ozone layer would expose the planet to heightened levels of ultraviolet rays, leading to a significant increase in skin cancer, cataracts, and other health issues for living organisms. The radiation could also disrupt ecosystems, affecting plant life by altering the conditions needed for photosynthesis and plant growth. In turn, this could destabilize food chains, putting all forms of life at risk. The idea that such catastrophic events could occur in our galaxy is unsettling, but scientists believe that the risk is low, yet it remains a fascinating area of study. These bursts offer a unique window into the extreme conditions of the universe, providing valuable insights into the most powerful forces at play in the cosmos. Understanding the mechanisms behind gamma-ray bursts not only expands our knowledge of astrophysical phenomena, but also deepens our appreciation of the fragility of life on Earth. Gamma-ray bursts, among the most energetic and violent events in the universe, have the potential to reshape our understanding of both cosmic phenomena and life on Earth. These catastrophic bursts, though rare, release an intense burst of energy that can have far-reaching consequences, both on a cosmic scale and right here at home. The immense power unleashed during these events can drastically elevate temperatures, triggering rapid atmospheric changes that could disrupt our planet's delicate balance. In the most extreme scenarios, gamma-ray bursts could lead to widespread extinction events, posing a grave threat not only to humans, but to all forms of complex life. The implications of such an event are profound. Understanding the dynamics of gamma-ray bursts isn't just about comprehending the sheer force behind these events. It's about preparing for a future where humanity is better equipped to face these cosmic threats. By delving deeper into the mechanics of these powerful bursts, we gain insights into the forces that drive them, unraveling the mysteries of how they occur and their potential to disrupt life on Earth. While gamma-ray bursts are infrequent occurrences, enhancing our monitoring technologies and building a comprehensive understanding of these phenomena can pave the way for better protection strategies, safeguarding our planet from such high-energy threats. Yet, the fascination with gamma-ray bursts extends beyond their destructive potential. These cosmic events serve as a reminder of the fragile balance that sustains life on Earth. They influence not just how we view the universe, but also how we approach our exploration of the cosmos. Each discovery brings us closer to understanding the universe's inner workings and the potential dangers that lie in wait. Gamma-ray bursts, with their extraordinary power, continue to be a key focus of astronomical research, both for their potential to shape our future and for the way they push the boundaries of human curiosity. In the broader context of space exploration, another critical phenomenon comes into play: cosmic rays. These high-energy particles travel across the vast expanse of space, originating from various sources such as the sun, supernovae, and even black holes. When cosmic rays collide with Earth's atmosphere, they trigger a cascade of secondary particles, some of which reach the planet's surface. Although cosmic rays are often associated with space exploration, their impact on life on Earth cannot be overlooked. For astronauts venturing beyond the protective shield of Earth's atmosphere, cosmic rays pose a serious health risk. Without the natural defense provided by Earth's atmosphere, astronauts in space are vulnerable to radiation, which can cause cellular damage and increase the likelihood of developing cancers and other radiation-induced illnesses. As humanity ventures further into space, particularly in missions to Mars or extended stays on the Moon, understanding and mitigating the risks posed by cosmic rays becomes crucial for ensuring the safety of astronauts. But the influence of cosmic rays extends beyond the confines of space travel. On Earth, cosmic rays contribute to the natural background radiation that we experience daily. Though our atmosphere and magnetic field shield us from most of their harmful effects, cosmic rays can still generate secondary particles that may influence weather patterns and cloud formation, potentially affecting our climate. These effects are still an area of active research, with scientists continually studying cosmic rays to track their sources, behavior, and develop new technologies to protect against their impact. Technological innovations, such as radiation shielding for spacecraft and real-time monitoring systems, play a critical role in addressing the challenges posed by cosmic rays. As our understanding deepens, these technologies will become even more vital for both protecting astronauts on long-duration missions and safeguarding life on Earth from the effects of these high-energy particles. Cosmic rays and their complex interactions with space exploration and the Earth's environment remind us of the interconnectedness of the universe. They highlight not only the challenges of venturing into space, but also the intricate dynamics that govern life on our home planet. Asteroids and comets, remnants from the early days of the solar system, add another layer of cosmic risk. Though they are fascinating objects of study, they also pose a significant threat to Earth. The primary danger lies in the potential for a collision with our planet. A large asteroid impact could unleash an amount of energy equivalent to millions of tons of explosives, resulting in catastrophic destruction. The aftermath could include massive wildfires, drastic shifts in climate, and even the extinction of entire species, as witnessed with the event that wiped out the dinosaurs. Such potential threats have led to a growing focus on planetary defense. In recent decades, scientists and researchers around the world have significantly enhanced efforts to monitor near-Earth objects, NEOs, asteroids, and comets that come close to our planet. By utilizing advanced telescopes and radar systems, astronomers track the paths of these objects, assessing their size, composition, and potential for future collisions. This proactive approach has led to global collaborations aimed at detecting and mitigating the risks posed by these celestial bodies. Various strategies are being developed, such as altering an asteroid's trajectory by impacting it with a spacecraft or employing a gravity tractor, a method where a spacecraft uses its mass to subtly shift the asteroid's orbit. Current missions aimed at testing these deflection techniques reflect the growing commitment to planetary defense. These missions focus not only on larger asteroids, but also on smaller ones, with the hope of developing effective solutions for a wide range of potential threats. By working together, nations and space agencies are taking steps to prepare for potential collisions and protect Earth from cosmic dangers. Solar flares, powerful bursts of energy emanating from the sun's surface, also present significant risks. These flares release waves of charged particles into space, creating geomagnetic storms that can disturb Earth's magnetic field. While solar flares are awe-inspiring in their energy, they can have serious repercussions for modern technology. The radiation released during these events can interfere with satellite communications, disrupt GPS signals, and even damage electrical grids on the ground. Similar to how a sudden change in weather can catch us off guard, solar flares can trigger abrupt shifts in the Earth's magnetic environment, leading to disruptions in critical technologies. The effects of solar flares are far-reaching. Satellites, for example, can experience signal degradation or complete loss of communication. GPS systems may provide erroneous readings, leading to navigation difficulties. The most concerning issue arises from the potential for geomagnetic storms to overload power systems, causing widespread blackouts. This is why monitoring solar activity is essential for modern infrastructure. By tracking solar flares in real time, scientists can issue early warnings, allowing satellite operators to temporarily shut down non-essential systems and power grid operators to adjust their networks to better absorb the added stress. Ultimately, the study of cosmic phenomena, whether it's gamma-ray bursts, cosmic rays, asteroids, or solar flares, has a dual purpose. Not only does it provide a deeper understanding of the universe, but it also equips us with the knowledge and tools to protect life on Earth from cosmic threats. With technological advancements and increased international collaboration, we are better prepared than ever to face the challenges posed by the cosmos. As our knowledge grows, so too does our ability to safeguard our planet and ensure the continued survival of all life. The challenge of strengthening the resilience of infrastructure has become more urgent than ever. This involves not just fortifying systems, but ensuring that they remain functional even in the face of the most unpredictable disturbances. For instance, upgrading power grid systems is essential to withstand sudden surges in energy. This could be achieved by reinforcing existing systems or introducing fail-safes that can take over when disruptions occur. In a world increasingly reliant on technology, investing in both real-time monitoring systems and infrastructure that can withstand future challenges is paramount. These measures are critical not only to reduce vulnerability, but to ensure that society continues to function smoothly, even when faced with natural phenomena like solar flares. Solar flares are an extraordinary example of cosmic events that can affect technology on Earth. These massive bursts of energy erupt from the sun, sending waves of radiation and charged particles toward our planet. But perhaps even more awe-inspiring and concerning are supernovae. A supernova occurs at the end of a massive star's life cycle, unleashing a catastrophic explosion of energy and matter into space. These events are some of the most spectacular fireworks the universe has to offer, but the prospect of a nearby supernova raises significant concerns for life on Earth. The potential for a supernova to explode within a few dozen light years of Earth is a scenario that, though rare, could have devastating effects. Such an event would release an enormous amount of radiation, including gamma rays. Gamma rays are the most energetic form of light, capable of traveling at the speed of light and penetrating through almost any material. If Earth were to be struck by these rays, the consequences could be catastrophic. The most immediate concern would be the damage to the ozone layer, which acts as our shield against the sun's harmful ultraviolet radiation. Without this protective layer, harmful UV rays would reach the Earth's surface, causing widespread harm to ecosystems and human health. In addition to gamma rays, a nearby supernova would also emit high-energy particles known as cosmic rays. These particles could collide with Earth's atmosphere, leading to secondary radiation effects. This increased radiation could impair the functioning of satellites and other technologies in orbit, disrupting communication networks and navigation systems that society increasingly relies upon. Even if a supernova occurs farther away, its shock waves could distort the interstellar medium, the material between the stars, potentially altering the composition of nearby cosmic clouds. These changes could have long-term implications, influencing the formation of new stars and the evolution of star systems, including our own. While the likelihood of a supernova erupting close enough to directly endanger life on Earth is low, the very possibility underscores the unpredictable nature of the universe. By studying these celestial phenomena, scientists can not only learn more about the stars that populate our cosmic neighborhood, but also gain insights into the delicate conditions that support life on our planet. Understanding such events helps us appreciate how vulnerable we are to the forces of nature, reminding us that our survival is intricately tied to the workings of the universe. Space weather, a term that refers to the conditions in space that can impact Earth, adds another layer of complexity to the challenge of safeguarding technology. Solar flares and coronal mass ejections, CMEs, are the two main drivers of space weather. These events involve the release of vast amounts of charged particles and energy into space, which can have significant effects not just on human space missions, but on the technologies we depend on here on Earth. One of the primary concerns during space weather events is the radiation exposure that astronauts face when solar particles collide with spacecraft. These high-energy particles can penetrate the hull of spacecraft, damaging sensitive instruments, disrupting communication systems, and compromising navigation systems. Space agencies therefore closely monitor solar activity and adjust mission parameters when solar activity is heightened. The International Space Station, ISS, for example, is equipped with special shelter areas where astronauts can take refuge during intense solar storms. Such precautions highlight the inherent risk of human exploration beyond Earth's atmosphere. For Earth, space weather has the potential to disrupt vital technological systems. When solar particles interact with Earth's magnetic field, they can cause geomagnetic storms. These storms can induce electric currents in the ground, damaging power grids and causing widespread blackouts. They can also affect satellite operations, leading to disruptions in satellite communications, GPS navigation, and the functioning of the satellites themselves. Additionally, these space weather events can alter atmospheric conditions, leading to the appearance of auroras at lower latitudes and disrupting radio communications, especially at higher frequencies. These phenomena underscore the interdependence of space and Earth systems, illustrating how even activities in the far reaches of space can have a profound impact on our daily lives. As we continue to rely on space-based technologies, understanding space weather has become crucial. Ongoing research and monitoring of solar activity are key to ensuring the protection of both space missions and the increasingly space-dependent infrastructure here on Earth. Meanwhile, space debris is a growing concern that presents significant risks to both current and future space missions. Imagine the vast expanse of space as a busy highway where satellites and spacecraft travel at unimaginable speeds. Now, picture this highway cluttered with debris, fragments from past missions, defunct satellites, and leftover rocket parts. These objects vary in size, from tiny flecks of paint to massive chunks of defunct machinery, and they're all traveling at velocities that can exceed the speed of a bullet. Even a tiny piece of debris colliding with an operational spacecraft could cause extensive damage, potentially crippling the spacecraft or leading to the loss of an entire mission. The problem is compounded by the increasing number of satellites being launched to meet the demands of global communication, navigation, and scientific exploration. As the number of objects in low Earth orbit (LEO) grows, so does the risk of collisions with space debris. At these high speeds, even the smallest fragment can wreak havoc on critical systems onboard satellites or crewed space vehicles. This not only threatens the safety of astronauts, but also jeopardizes the vital data and services that these spacecraft provide. As the congestion in LEO continues to rise, the need for effective solutions to manage space debris becomes more urgent. Without proper measures in place to track, remove, or minimize debris, space missions could face an increasingly hazardous environment. The future of space exploration relies not only on the advancement of technology, but also on our ability to manage and protect the space around our planet. Moreover, the problem of space debris is self-perpetuating, creating a dangerous feedback loop. A single collision in orbit can generate a cascade of additional fragments that contribute to the ever-growing cloud of debris surrounding Earth. This, in turn, escalates the risk to spacecraft and satellite operations, making protective measures progressively more difficult to implement. The issue is not just a passing concern. It is a fundamental challenge that must be confronted head-on, particularly as we look toward the future of space exploration. Future space missions, especially those aiming for deep space exploration, will inevitably face the daunting task of dealing with the growing threat of debris. Effective tracking of these objects is critical for ensuring the safety of operational spacecraft. Alongside this, developing advanced technologies to mitigate their impact becomes a necessity. One of the key strategies for this is the employment of innovative satellite designs, incorporating advanced shielding to withstand potential collisions. Additionally, mechanisms to safely deorbit defunct satellites will play a crucial role in reducing the overall amount of debris in orbit. By taking these proactive steps, we can significantly enhance the safety of operations in space. Every action taken to address space debris not only protects current missions, but also lays the foundation for secure future exploration of the cosmos. However, space travel is not just a technical endeavor. It is also an extraordinary human challenge. Long-term space missions present a multitude of psychological and physical hurdles for astronauts. Physically, the absence of Earth's gravitational pull leads to a range of issues. Without gravity constantly acting on their bodies, astronauts experience muscle atrophy and bone loss. The lack of weight-bearing activity in space leads to weakened muscles and decreased bone density, conditions that can be particularly severe if not addressed. Astronauts must engage in rigorous exercise routines to maintain their physical strength and cardiovascular health. This is not only essential for their physical well-being, but also necessary for their ability to carry out their demanding tasks in space. Additionally, the environment of space disrupts the vestibular system, which helps maintain balance and spatial orientation. This disruption often results in what is colloquially known as space motion sickness, a condition that causes discomfort and disorientation, especially in the early stages of a mission. Astronauts may struggle with nausea, dizziness, and other symptoms as their bodies adjust to the absence of gravity. Furthermore, the confined environment of a spacecraft or space station can cause the body's circadian rhythms to falter, leading to sleep disturbances. Without the natural light and daily routines that regulate sleep on Earth, astronauts can experience significant challenges in maintaining a healthy sleep cycle. This disruption can have a negative impact on their mood, cognitive functions, and overall performance on the mission. Psychologically, the isolation and confinement of space travel create their own set of challenges. Astronauts are cut off from their familiar environments and loved ones for extended periods, sometimes for months at a time. This isolation can lead to feelings of loneliness and homesickness, which can have a profound impact on mental health. The pressure of working in such a high-stakes environment, combined with the necessity for close cooperation with a small group of colleagues in tight quarters, can also result in stress. Personalities can clash and conflicts can arise, especially in situations where tension and stress levels are high. To combat these psychological stresses, astronauts engage in structured routines, social activities, and creative outlets to maintain their mental health. Regular communication with loved ones back on Earth, even if it is delayed, provides vital emotional support. Furthermore, having access to recreational activities and time set aside for individual pursuits helps astronauts cope with the stresses of long-term space travel. These coping mechanisms underscore the need for comprehensive psychological training and continuous support throughout their journeys. As we venture further beyond our home planet, these mental and physical challenges will remain central to the success of space exploration. Beyond the immediate concerns of astronaut health and safety, there is also the broader issue of planetary defense, which plays a crucial role in protecting Earth from potential asteroid and comet impacts. These impacts, if left unaddressed, could have devastating global consequences. Earth is a small, fragile oasis drifting through the vast expanse of space, surrounded by debris left over from the formation of the solar system. Occasionally, some of this debris, in the form of large rocks or comets, may drift into our orbital path. If one of these objects were to collide with Earth, the consequences could be catastrophic. Planetary defense missions focus on detecting, tracking, and characterizing near-Earth objects, asteroids and comets that approach our planet's orbit. Early detection is critical, as it provides the time necessary for scientists to analyze these objects. Understanding their size, composition, and trajectory is vital for assessing the potential risk they pose. Monitoring them over time allows scientists to calculate their paths and predict future encounters with Earth. However, detection alone is not sufficient. Once a potential threat is identified, planetary defense strategies must be put into action. One potential strategy involves sending a spacecraft to collide with an asteroid at high speed, altering its trajectory. Even a small change in the object's path could significantly reduce the risk of impact with Earth. Other strategies might involve using the gravitational pull of a spacecraft to gradually alter the course of a threatening object. These methods, while still theoretical in some respects, are actively being studied and developed. In addition to these active measures, planetary defense missions also focus on raising public awareness and preparedness. By educating the public about the potential threats posed by near-Earth objects, these missions foster international cooperation and the development of contingency plans. The stakes are incredibly high, and these planetary defense efforts remind us of the responsibility we bear to protect our planet from the dangers that lurk in the cosmos. It is a reminder that we must make informed decisions about our planet's safety, not just for today, but for future generations to come. Finally, there are the enigmatic fast radio bursts, FRBs, bursts of radio waves that last only a few milliseconds but release energy equivalent to what the sun emits over several days. These mysterious cosmic signals have captivated scientists who are still trying to unlock their secrets. The first FRB was detected in 2007, and since then, many more have been observed, each raising new questions about their origin and nature. One of the biggest mysteries surrounding FRBs is their extreme brightness, suggesting they originate from sources of incredible power. Unlike most natural astrophysical phenomena, which vary in intensity, FRBs seem to maintain a consistent brilliance, indicating that something extraordinary is taking place. Adding to the mystery, FRBs appear to occur at random, with no clear pattern in their occurrence or location in the sky. Potential explanations for their origin range from the plausible to the exotic. One leading theory posits that they may be caused by neutron stars, specifically magnetars. These dense, highly magnetic remnants of supernova explosions might unleash bursts of energy, producing the radio waves that we detect here on Earth. While this theory offers some plausible answers, the true origin of FRBs remains elusive, and the search for an explanation continues to intrigue scientists across the globe. However, this explanation does not fully account for all of the observed fast radio bursts, FRBs, particularly those that appear to repeat. One alternative theory is that these bursts might originate from more exotic sources, pushing the boundaries of what we understand about the cosmos. Some scientists speculate that the bursts could be the result of cataclysmic cosmic events, such as the violent collisions of black holes, while others entertain the possibility that these signals are artificially created, potentially even by advanced technological civilizations from other worlds. While the idea of extraterrestrial communication ignites the imagination of many, it remains a speculative theory, far from accepted within the scientific community. Fast radio bursts, with their puzzling characteristics, represent one of the most captivating enigmas in the field of astrophysics. These signals, known for their extreme brightness and unpredictable nature, have become a focal point of intense research. As technology advances and new detection methods are developed, scientists are inching closer to uncovering the mysteries behind these enigmatic signals. In doing so, they hope to not only understand where they originate, but also gain a deeper understanding of the fundamental workings of the universe itself. Unidentified cosmic radio signals, often referred to as radio transients, exhibit a fascinating range of characteristics that have drawn the attention of astronomers worldwide. These signals can come from vast distances, far beyond our own solar system, and present unique attributes that set them apart from more familiar cosmic phenomena. One of the most intriguing features of these signals is their fleeting duration. Many of them are incredibly short bursts, often lasting only a fraction of a second. Despite their brief existence, they carry immense energy, making them incredibly bright. These ephemeral signals, by their very nature, are difficult to detect and study. Their transients pose significant challenges for scientists in terms of protection and analysis, requiring rapid observation and highly sensitive equipment. Some of these bursts repeat periodically, adding a layer of regularity to their otherwise erratic behavior, while others appear sporadically, leaving no discernible pattern. This unpredictability only deepens the mystery of their origin. Could these bursts be the result of some rare cosmic event, or might they have a more mundane explanation that we've yet to uncover? Additionally, the frequency range of these signals sets them apart from typical radio broadcasts, which are usually confined to a narrow spectrum. Cosmic radio signals, in contrast, span a much broader range of wavelengths, suggesting that their sources might be highly varied or involve complex mechanisms yet to be fully understood. This diversity in signal characteristics opens up a wealth of possibilities for their origins. They could be the result of phenomena as exotic as the interactions of dark matter, or they might emanate from the intense environments surrounding neutron stars or black holes. Some scientists have even proposed the idea that these signals could be the result of interactions involving other, as yet undiscovered, particles or forces. Another important characteristic of these signals is their polarization. The electromagnetic waves associated with them can oscillate in different orientations, providing vital clues about the physical processes involved in their creation. By studying the patterns of polarization, researchers can gain insights into the conditions surrounding the sources of these signals, further refining our understanding of the cosmic environment from which they originate. In addition to polarization, the dispersion of these signals is an intriguing feature. As radio waves travel through interstellar space, they encounter various particles and magnetic fields that cause delays in their arrival. Different frequencies arrive at different times due to this phenomenon, a process that adds yet another layer of complexity to the study of these signals. By carefully analyzing how the signals are dispersed, scientists can infer crucial details about the interstellar medium, such as the density of particles or the presence of magnetic fields along the path the signal travels. Ultimately, the source of these cosmic radio signals remains one of the most perplexing aspects of their study. While some bursts have been traced back to known astrophysical objects, many others remain unassociated with any identifiable source. This has led to much speculation about their origin. Could they be the remnants of ancient supernovae, or could they represent emissions from exotic stars at the ends of their life cycles? Or might they even be something entirely different, perhaps a form of technological communication from distant extraterrestrial civilizations? With so many possibilities and so few concrete answers, the study of these signals remains a rich area of research, with each new discovery acting as a piece of a vast cosmic puzzle, inviting scientists to explore deeper and further into the unknown reaches of the universe. As scientists continue to probe these cosmic mysteries, they are also investigating the fundamental question of dark matter, a substance that, despite its name, cannot be directly observed but whose presence is inferred by its gravitational effects. Understanding dark matter is crucial for explaining the larger scale workings of the universe. Through a combination of observational techniques and theoretical models, astronomers are piecing together the enigma of dark matter. One of the primary ways scientists study dark matter is by examining its effects on the motion of galaxies and galaxy clusters. When astronomers observe galaxies, they note that the visible matter, such as stars and gas, does not provide enough mass to account for the observed speeds at which these galaxies rotate. Instead, they detect an invisible component that is believed to be dark matter, exerting a gravitational pull strong enough to hold the galaxies together. Another key method of studying dark matter involves gravitational lensing, a phenomenon where the presence of large amounts of dark matter bends the light from objects behind it. This bending distorts the images of distant galaxies, allowing scientists to map the distribution of dark matter in a given region of space. By carefully studying these lensing effects, researchers can infer the amount and distribution of dark matter present, providing critical data for their understanding of how dark matter influences the structure of the universe. Researchers also turn to the cosmic microwave background radiation, the residual glow from the Big Bang, as a tool for studying dark matter. This radiation, which permeates the universe, offers valuable information about the large-scale structures of the cosmos and the evolution of the universe itself. By analyzing the patterns and fluctuations in this radiation, scientists can learn more about how dark matter has contributed to the formation and evolution of galaxies, stars, and other cosmic structures over time. Understanding dark matter is not just important for explaining the motion of galaxies or the distribution of cosmic structures, it is crucial for advancing our understanding of gravity itself. Dark matter challenges and extends our current models of physics, pushing the boundaries of both Newtonian mechanics and Einstein's theory of general relativity. While these traditional theories of gravity work well for explaining the behavior of visible matter, they struggle to account for the observed phenomena involving dark matter. Thus, unraveling the nature of dark matter is a key step toward developing a more comprehensive theory of gravity, one that incorporates both visible and invisible matter in a more unified framework. As we continue to study these mysterious signals and the unseen forces shaping the universe, we move ever closer to the kind of profound insights that could transform our understanding of reality. The combination of advanced technology, detailed observations, and innovative theoretical models may one day reveal the true nature of dark matter, the origin of fast radio bursts, and even the fundamental forces that govern the universe on every scale. However, the presence of dark matter in the universe suggests that our understanding of its structure and behavior remains incomplete. This mysterious substance, which cannot be seen directly, influences the formation and movement of galaxies, and as such, studying it presents a pivotal opportunity for scientists to refine their theories. By investigating dark matter, we can enhance our understanding of gravity's role in the larger framework of cosmology, providing deeper insights into fundamental questions about the universe's origin and evolution. This quest not only aims to reveal how galaxies form and evolve over cosmic timescales, but it also offers glimpses into the early moments of the universe, just after the Big Bang. The more we learn about dark matter, the clearer the picture becomes, stretching from the behavior of subatomic particles all the way to the vast, massive structures that form the very fabric of the cosmos. By exploring the mysteries of dark matter, scientists may begin to unravel the complex, interconnected web that governs everything from the tiniest particles to the most colossal cosmic entities. At the heart of this inquiry lies the cosmic microwave background radiation, CMB, often considered a cornerstone of our understanding of the universe. To visualize this, imagine the universe as an intricate tapestry, intricately woven together over eons. It all began with the Big Bang, a single explosive event that set the cosmos into motion. As the universe began to expand and cool, it released vast amounts of energy, first in the form of heat and light. Over billions of years, this energy has stretched and cooled, eventually transforming into the faint afterglow we now observe as microwave radiation. The CMB is significant because it holds vital information about the early universe, offering a snapshot of the cosmos only a few 100,000 years after its formation. In its infancy, the universe was a hot, Dense plasma, a chaotic soup of particles that interacted with one another incessantly. As it expanded and cooled, conditions became suitable for protons and electrons to combine into neutral hydrogen atoms. This crucial event, known as recombination, allowed light to travel freely for the first time, creating the background radiation we detect today. When scientists study the CMB, they observe a near-uniform glow across the entire sky, punctuated by minuscule fluctuations in temperature. These tiny variations are not random. They hold a treasure trove of information about the early universe. The fluctuations point to the distribution of matter and energy in the cosmos at that time, offering key clues about how the large-scale structure of the universe evolved. By analyzing these subtle temperature shifts, cosmologists can deduce details about the formation of galaxies, clusters of galaxies, and other large-scale structures over time. The CMB also provides a robust confirmation of the Big Bang theory, aligning with predictions made about the universe's evolution. It acts as the critical evidence validating the cosmological model that explains how the universe began and continues to unfold. Not only does the CMB illuminate the past, but it also serves as a guide for understanding the future of the cosmos. For cosmologists, this radiation is an indispensable tool, helping them piece together the grand narrative of the universe's history and offering hints about the forces that will shape its destiny. Another breakthrough discovery that has revolutionized our understanding of the universe comes in the form of gravitational waves, ripples in the fabric of space-time itself. These waves are generated by some of the universe's most violent and energetic events, such as the collision of black holes or the merging of neutron stars. Imagine standing at the edge of a calm lake. When you throw a stone into the water, ripples spread outward from the point of impact. In much the same way, when massive cosmic objects accelerate or collide, they disturb space-time, producing waves that travel across vast stretches of the universe. These gravitational waves are incredibly significant because they carry crucial information about their origins. Unlike light, which can be absorbed, scattered, or blocked by interstellar matter, gravitational waves pass through obstacles with ease, providing an unobstructed view of events that occurred far in the past. This makes them a powerful tool for studying cosmic phenomena that were previously invisible to traditional telescopes. Gravitational waves open an entirely new chapter in astrophysics. With this detection method, scientists are able to hear cosmic events that would otherwise remain silent to optical telescopes. For instance, the collision of two black holes generates a strong gravitational wave signal that cannot be captured by traditional methods. By analyzing these waves, scientists can gather critical data about the masses, spins, and distances of the objects involved, as well as explore the very nature of gravity itself. These waves also provide unique insights into the early universe, as gravitational ripples, from moments shortly after the Big Bang, may encode information about the very structure of space-time in its infancy. By studying these ancient waves, researchers hope to unlock secrets of cosmic evolution that stretch far beyond what can be inferred from light alone. Gravitational waves serve as a complementary tool to existing methods of observation, allowing us to piece together the intricate puzzle of cosmic history that is otherwise hidden from view. They reveal a wealth of information about the forces that shape the universe and offer a new way to explore fundamental physics, bringing us closer to understanding the very fabric of reality itself. And then there is the Fermi paradox, a thought-provoking dilemma that has intrigued scientists and philosophers alike for decades. Named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox highlights the apparent contradiction between the high probability of extraterrestrial civilizations existing in the vast universe and the complete lack of evidence for their presence. Given the sheer scale of the cosmos, it's hard to imagine that Earth is the only planet capable of supporting life. There are billions of stars in our galaxy alone, and many of these stars are likely orbited by planets that could harbor life, perhaps even intelligent life. Considering the age of the universe, it is plausible that some of these planets may have developed advanced civilizations long before humanity ever came into existence. One would expect that if intelligent life is indeed common, we should be able to detect signs of its presence. Whether through direct contact, radio signals, or other technological markers, we should be able to detect the faintest whisper of their existence. And yet, despite the countless stars, the vast number of potentially habitable planets, and the billions of years of cosmic evolution, we have yet to find any conclusive evidence that we are not alone. The Fermi paradox thus raises profound questions about the nature of life in the universe. Could it be that intelligent civilizations are rare, or perhaps that they tend to self-destruct before they reach the level of technological advancement required to communicate across vast interstellar distances? Or is it possible that we are simply looking in the wrong way, using the wrong methods, or at the wrong time? This enigma challenges our understanding of life, intelligence, and our place in the universe, and it serves as a powerful reminder that there is still so much more to discover about the cosmos. Despite decades of intensive scientific exploration and observation, one critical expectation remains unmet. Humanity has yet to detect definitive signals or artifacts from any extraterrestrial civilizations. This lack of evidence has left many perplexed, raising profound questions about the nature of intelligent life itself. If the universe is so vast, with countless potential habitats for life scattered across the cosmos, why have we not encountered any advanced civilizations? Where are the others, and what explains our profound solitude in this immense expanse of space? Several theories have been proposed to address this paradox, but none can fully explain the absence of extraterrestrial contact. One compelling idea is that intelligent life is extraordinarily rare. Perhaps the conditions required for advanced civilizations to emerge are so specific, so narrowly defined, that the chances of them occurring anywhere in the universe are incredibly slim. In this view, the emergence of such civilizations might require a combination of factors, such as the right planetary conditions, the right chemical elements, and an extraordinarily stable environment that rarely align. Another theory is that technological civilizations tend to self-destruct or collapse before they can make contact with others. This hypothesis suggests that the very technologies that allow civilizations to thrive also carry the potential for their downfall. Whether through warfare, environmental destruction, or some other unforeseen consequence, civilizations may reach a point where they are no longer capable of communication with other intelligent species, or even of surviving long enough to make contact. Alternatively, it is possible that advanced civilizations are actively avoiding us. Perhaps they have recognized that contact with less developed species could lead to harm, either to themselves or to us. Some speculate that these civilizations have deliberately chosen not to reveal themselves for reasons ranging from self-preservation to ethical considerations. It could also be that the civilizations we seek are so different from us, whether in their biology, technology, or ways of communication, that we simply do not recognize their presence, even if their signals are all around us. Ultimately, the Fermi paradox forces us to confront our assumptions about the nature of life and intelligence in the universe. It compels us to reconsider our definitions of civilization and technological advancement, while challenging our expectations for what an advanced society might look like. This mystery invites deeper exploration into why we have yet to encounter any other intelligent beings, and what this means for our place in the universe. One of the many anomalies that has intrigued scientists is the Pioneer anomaly, which refers to the unexpected changes in speed experienced by the Pioneer spacecraft as they ventured through the outer reaches of our solar system. Launched in the early 1970s, the Pioneer spacecraft were part of an ambitious effort to study the distant corners of our solar system, sending back invaluable data from the farthest reaches of space. However, as they continued their journey, researchers began to notice a curious phenomenon. The spacecraft were drifting off course, moving at speeds that deviated from predictions based on the known gravitational influences of the Sun and other celestial bodies. The discovery of this anomaly sparked a flurry of investigation. Scientists initially focused on examining the trajectory data, meticulously analyzing each small deviation in speed. As they studied the spacecraft's path, they considered various possible explanations. One of the most intriguing hypotheses revolved around the heat generated by the spacecraft's own power systems. The Pioneer spacecraft were equipped with radioactive isotopes that emitted energy, which was then dispersed into space. The distribution of this heat was not perfectly uniform, and researchers speculated that the uneven distribution could create a small but measurable thrust, enough to slightly alter the spacecraft's trajectory. In response to this theory, scientists conducted extensive research into the thermal properties of the spacecraft, hoping to determine whether this uneven heat distribution could account for the anomaly. Despite the compelling nature of this explanation, other theories began to emerge, suggesting that unknown gravitational forces, perhaps from dark matter or other factors not yet understood, could be influencing the spacecraft's motion. To test these ideas, scientists used advanced computer simulations and theoretical models to explore how such forces might manifest in the spacecraft's trajectory. These models were refined over years of collaboration between researchers around the world. Despite numerous attempts to explain the anomaly, the cause of the Pioneer anomaly remains elusive, and the mystery continues to fuel scientific inquiry. Nevertheless, the investigations surrounding the Pioneer anomaly have not been in vain. While the exact cause remains uncertain, the research has provided valuable insights into the fundamental laws of gravitational physics. It has deepened our understanding of space travel, and in many ways, it has guided future missions as they prepare to journey into the more unexplored regions of the cosmos. Every piece of evidence gathered brings us closer to unlocking the mysteries of space and the laws that govern it. Another captivating cosmic mystery is that of Tabby's star, officially designated KIC 8462852. This star has fascinated astronomers due to its peculiar and unpredictable dimming patterns. Unlike most stars, which exhibit steady, gradual changes in brightness, Tabby's star shows erratic fluctuations, with occasional dramatic drops in brightness over unpredictable intervals. The behavior of this star has prompted a host of questions about the nature of its planetary system and what might be causing these strange variations. One theory that scientists have considered is the presence of a swarm of comet-like bodies orbiting the star. As these comets approach the star, they release gas and dust, which forms a cloud around the star. This cloud of particles could block some of the star's light, explaining the temporary dimming observed by astronomers. However, this explanation doesn't entirely satisfy the mystery. The sheer scale and variability of the dimming events suggest that the presence of comets alone might not fully account for the observed behavior. Another intriguing possibility is that the dimming could be caused by a large planet, or perhaps several planets with unusual orbits. In a multi-body system, gravitational interactions between the star and surrounding objects could lead to shifts in the orbits of the planets and other bodies, which in turn might cause significant changes in the star's light. These dynamic, chaotic interactions between celestial objects often lead to unexpected behaviors, and Tabby's star may be an example of just such a phenomenon. Even more speculative theories have been proposed, including the possibility that the dimming could be caused by artificial structures around the star. Some have suggested the idea of a Dyson sphere, a massive, hypothetical structure built by an advanced civilization to capture the energy output of the star. While this idea remains far outside the realm of mainstream science, it serves as a reminder of how Tabby's star continues to spark the imagination of scientists and the public alike. Its strange behavior challenges our current understanding of stellar dynamics and reminds us how much there is still to learn about the universe. In addition to these mysteries, the discovery of new elements within stars and interstellar mediums continues to be a fascinating area of study. Stars function as cosmic furnaces, where the extreme heat and pressure allow nuclear fusion to occur. Through this process, lighter elements combine to form heavier ones, and over the course of a star's life, it can produce elements ranging from helium to iron. When massive stars reach the end of their lives, they explode in spectacular supernovae. These explosions not only release the elements created during the star's life, but also forge even heavier elements, such as gold and uranium, through a process known as rapid neutron capture. Although the discovery of entirely new elements, those not yet recognized by science, is exceedingly rare, the study of these processes offers insight into the very foundations of matter. The periodic table contains a finite number of elements, with heavier elements being synthesized in laboratories under extreme conditions. Discovering new elements in stars depends on whether they can form and survive under the unique conditions present in the stellar interior, without decaying into lighter elements. As scientists continue to probe the depths of space, exploring the mysteries of the Pioneer Anomaly, Tabby's star, and the origins of the elements, one thing remains clear. The universe is full of unexpected phenomena, each one challenging our understanding of the cosmos. And with every new discovery, we move one step closer to understanding not just the intricate workings of distant stars, but the very nature of the universe itself. Advancements in technology, particularly in the field of spectroscopy, the study of how light interacts with matter, have revolutionized our ability to identify and analyze the elemental composition of stars and other celestial bodies. Through these innovations, scientists can detect the unique fingerprints of elements based on the specific light they emit or absorb. Every element has a distinct pattern in its interaction with light, creating what is essentially a cosmic barcode that researchers can read to uncover the secrets of distant stars, galaxies, and nebulae. The processes occurring within stars and the interstellar medium lead to the creation of a broad array of elements, from the lightest atoms like hydrogen to the heavier ones formed in supernova explosions. While these processes give rise to a wide range of elements, the discovery of completely new elements remains unlikely. However, the diversity of these elements, their varying structures, behaviors, and abundances, provides us with crucial insights into the workings of the universe. This knowledge deepens our understanding of nuclear physics, while also expanding our comprehension of astrophysics, the study of celestial objects and phenomena. The tools that enable these discoveries, particularly telescopes, have seen remarkable progress over the years. Imagine the early astronomers peering through rudimentary lenses, seeing only faint points of light scattered across the vast dark canvas of the night sky. These simple instruments, though groundbreaking at the time, provided limited information. As technology advanced, so too did the sophistication of telescopes. Today's state-of-the-art instruments employ large mirrors, intricate optics, and innovative designs to gather more light than ever before, allowing us to observe objects that were once invisible to the human eye. Modern telescopes are no longer confined to observing just visible light. They are equipped with the capability to detect wavelengths beyond the visible spectrum. This multi-wavelength approach is essential for understanding the full range of phenomena in space. For instance, cooler and dimmer regions of space that emit infrared light can be studied, revealing hidden structures that are otherwise obscured. On the other end of the spectrum, high-energy environments, such as those around black holes, emit X-rays, which can be captured and analyzed to understand their violent and dynamic nature. Each type of light provides a different perspective, offering a more complete and nuanced picture of the universe's vast and varied processes. Moreover, advancements in adaptive optics have dramatically improved the clarity of observations. The Earth's atmosphere, with its turbulent air and shifting temperatures, can blur and distort the images captured by telescopes. Before adaptive optics, even the most powerful observatories on the ground struggled to deliver clear views of distant galaxies or the intricate structures of nebulae. Now, through real-time adjustments to the telescope's mirror systems, astronomers can correct for these atmospheric distortions, enabling them to observe with unprecedented sharpness and precision. This technology has opened up new frontiers for studying the cosmos with an accuracy that was previously unattainable. Space-based telescopes, such as those launched beyond Earth's atmosphere, have taken this further. Freed from the limitations imposed by our planet's atmosphere, these instruments can produce incredibly sharp images and gather high-quality data across multiple wavelengths. By doing so, they have led to groundbreaking discoveries, such as the detection of exoplanets, planets orbiting stars outside our solar system, and a more detailed mapping of cosmic background radiation. These observations have provided deeper insights into the life cycles of stars, the evolution of galaxies, and the elusive behavior of dark matter. Each discovery pushes the boundaries of what we know and invites us to ask deeper, more complex questions about the universe. The continuous progress in telescopic technology has not only expanded our ability to view and understand deep space, but has also accelerated our exploration of fundamental astrophysical processes. For instance, understanding the formation of galaxies, the behavior of black holes, and the intricate relationships between visible and dark matter has become much more achievable. With every technological leap, humanity is not just gaining a broader view of the cosmos, but also expanding its curiosity and thirst for knowledge. In this age of technological marvels, artificial intelligence, AI, has emerged as an indispensable ally in the field of astrophysics. AI is revolutionizing the way scientists process and interpret the vast amounts of data generated by telescopes and other observational tools. The sheer volume of data produced by modern astronomical missions, ranging from images of far-off galaxies to signals potentially indicating the presence of exoplanets, can be overwhelming. AI algorithms, however, are perfectly suited for handling such massive data sets, as they can quickly analyze and make sense of this information in ways that would be impossible for human researchers alone. One of the most significant contributions of AI to astrophysics is its ability to identify patterns in the data that may go unnoticed by humans. Machine learning, a subset of AI, has been particularly useful in classifying astronomical objects. For example, AI systems can distinguish between different types of stars, galaxies, and even detect exoplanets with remarkable precision. These algorithms are trained on vast data sets, learning to recognize specific features and characteristics, enabling them to make predictions about new data. This not only accelerates the pace of discovery, but also allows scientists to focus on the most promising areas of research, rather than spending time manually sorting through countless images and data points. By partnering with AI, astronomers can tackle some of the most complex questions about the universe with greater speed and accuracy. Whether it's mapping the distribution of galaxies across vast cosmic distances, studying the intricacies of stellar formation, or searching for signs of life beyond our solar system, AI is proving to be an invaluable tool in the ongoing quest to understand the universe in all its complexity. As we continue to push the boundaries of technology, from enhanced telescopic capabilities to the integration of artificial intelligence, our capacity to explore the cosmos grows exponentially. Every discovery builds upon the last, creating a continuous cycle of learning, innovation, and exploration. With each leap forward, we are not merely expanding our view of the stars, we are deepening our understanding of the very nature of the universe itself. The mysteries that once seemed beyond our grasp are now being uncovered, inviting us to explore realms and questions we once thought impossible to answer. Artificial intelligence, AI, is playing an increasingly pivotal role in transforming astrophysics, enabling breakthroughs that were once beyond the grasp of traditional scientific methods. One of the key contributions AI makes is in the modeling of complex astrophysical phenomena, from simulating the formation of stars to unraveling the intricate dynamics surrounding black holes. By harnessing AI tools, researchers are able to create simulations that are not only more accurate but also far more detailed. These simulations are critical in exploring the forces that shape our universe and advancing our understanding of how it evolves over time. In addition, AI aids in the automation of discovering new celestial bodies. By training algorithms on vast data sets from previous astronomical observations, AI can predict where to look and under which conditions new discoveries are likely to emerge. This proactive, data-driven approach is accelerating the pace at which astronomers make new discoveries, vastly improving the efficiency and depth of cosmic exploration. Artificial intelligence is reshaping the landscape of modern astrophysics by facilitating faster data analysis, enhancing classification accuracy, refining simulations, and streamlining the discovery process. With AI at the forefront, our journey to comprehend the universe is becoming not only more efficient, but also more profound, paving the way for insights that once seemed impossible to reach. The integration of AI into astrophysical research is making previously insurmountable challenges more manageable, providing humanity with tools to probe deeper into the mysteries of the cosmos. Moreover, the rise of quantum computing is poised to revolutionize how we simulate and understand the most elusive cosmic phenomena. At the heart of quantum computing lies the principles of quantum mechanics, which govern the behavior of particles at incredibly small scales. This allows quantum computers to process vast amounts of data simultaneously, leveraging parallelism in a way classical computers simply cannot match. The computational demands of simulating complex cosmic systems, such as modeling the behavior of black holes, the formation of galaxies, and the elusive properties of dark matter, can be overwhelming for traditional computers, which often result in approximations that fail to fully capture the intricacies of these phenomena. In contrast, quantum computers can explore a multitude of potential states at once, dramatically accelerating the pace at which researchers can run these simulations. By doing so, they can tackle problems that would otherwise take years, if not decades, to solve with conventional computing methods. Imagine the vast undertaking of modeling the universe's evolution from the Big Bang to the present day. A quantum computer, capable of modeling billions of particles and the forces acting upon them, could provide unprecedented insights into how cosmic structures like galaxies, stars, and planets were formed, and how they have evolved over time. Quantum computing also has the potential to advance our understanding of fundamental physics, including the very nature of space-time itself. By simulating quantum fields that form the foundation of cosmic behavior, scientists are poised to uncover entirely new theoretical frameworks. These breakthroughs could provide deeper insights into the mysteries of dark energy, the acceleration of the universe's expansion, and other unresolved questions that have puzzled physicists for centuries. As quantum computing technology matures, it promises to unlock new possibilities for astrophysics, empowering researchers to delve into realms of discovery that were previously unimaginable. As these technological advancements unfold, they may allow us to unravel the complex interconnectedness of cosmic phenomena in ways we have never before dreamed possible. This, in turn, could lead to an era of profound understanding of the universe and our place within it. The dream of interstellar travel has long captured the human imagination, with scientists and dreamers alike pondering the possibilities of exploring distant star systems. A variety of innovative concepts are now emerging, each offering new paths to reach the stars. One such breakthrough is the idea of solar sails. These are large, reflective surfaces designed to capture the pressure of sunlight and use it to propel a spacecraft forward. Similar to a sailboat harnessing the wind, solar sails capture the momentum of photons emitted by the sun. This method of propulsion could enable spacecraft to gradually build up speed over time, potentially reaching other star systems within a human lifetime. Another area of promising research focuses on using nuclear fusion for propulsion. This approach envisions spacecraft powered by fusion reactions, the same process that fuels the sun. By fusing light atomic nuclei to release immense amounts of energy, these spacecraft would generate continuous thrust, opening up the potential for faster travel across vast distances. A fusion-powered spacecraft would essentially contain a compact star, offering the sustained energy necessary for interstellar travel. Nuclear propulsion is another technology that has sparked interest among researchers. Using nuclear fission or fusion to produce thrust, this propulsion method promises a more efficient way to achieve the high speeds required for interstellar travel. The key advantage of nuclear propulsion is its ability to generate a powerful, consistent force over long periods of time, which would drastically shorten the travel time to neighboring star systems. Perhaps one of the most tantalizing concepts in the realm of interstellar travel is the idea of warp drives. By manipulating the fabric of space itself, a warp drive could theoretically create a bubble of space-time that contracts in front of a spacecraft while expanding behind it, allowing the vessel to travel faster than the speed of light. This concept, while still firmly in the realm of theory, has sparked extensive scientific discussion and exploration into how we might one day make faster-than-light travel a reality. Additionally, advancements in artificial intelligence and robotics are set to play a critical role in the success of interstellar missions. These technologies could autonomously manage spacecraft operations over the long durations of space travel, allowing humans to focus on exploration while minimizing the risks associated with deep space voyages. The integration of AI and robotics could also be crucial for supporting human crews on extended missions, enabling them to conduct research, maintain equipment, and navigate the challenges of space exploration with unprecedented precision. Together, these technological breakthroughs represent more than just advances in our ability to travel through space. They mark a profound shift in how we approach the exploration of the cosmos. Each of these innovations brings us one step closer to the day when we can venture beyond our solar system, uncovering the mysteries of distant worlds and perhaps one day discovering signs of life beyond Earth. As humanity continues to push the boundaries of space exploration, the future of interstellar travel is unfolding before our eyes. Fueled by creativity, innovation, and the enduring human spirit of discovery, these advancements hold the potential to reshape our understanding of the universe and transform the way we explore the stars. In parallel, the James Webb Space Telescope, JWST, represents a revolutionary leap forward in our quest to understand the cosmos. While the Hubble Space Telescope has been a cornerstone of astronomical observation, the JWST offers a fundamentally different approach. Unlike Hubble, which primarily observes ultraviolet and visible light, the JWST focuses on infrared wavelengths. This shift is crucial because infrared light can penetrate dense clouds of gas and dust that often obscure the view of distant astronomical phenomena, revealing objects and events that were previously hidden from view. One of the key advantages of the JWST is its large mirror, which allows it to capture significantly more light than previous telescopes. This increased sensitivity enables the telescope to observe fainter and more distant objects, including some of the earliest galaxies formed after the Big Bang. This capability is particularly important for studying the formation and evolution of stars, as well as exploring the atmospheres of exoplanets. By offering a clearer, more detailed view of the universe, the JWST is poised to open new frontiers in our understanding of the cosmos, helping scientists probe deeper into the mysteries of our origins and our place in the universe. The vast expanse of space has long been a source of fascination and intrigue, but only in recent decades have we truly begun to unlock its secrets with advanced technology. One of the most remarkable tools in this ongoing exploration is the James Webb Space Telescope, JWST, a marvel of engineering that allows us to probe the deepest corners of the universe. With its cutting-edge capabilities, the JWST has revolutionized our understanding of the cosmos, enabling astronomers to examine distant celestial bodies in ways previously thought impossible. At the heart of the JWST's capabilities lies its advanced technology for spectroscopy, a method that breaks down the light emitted by stars and other objects into its constituent colors. This technique provides a wealth of information about the chemical composition of distant worlds. Through this process, we gain insights not only into the makeup of faraway planets, but also into the possibility of life elsewhere in the universe. Spectroscopy helps scientists analyze the atmospheres of exoplanets, offering clues about whether these distant worlds could support life. It also plays a crucial role in understanding the complex processes that govern the life cycle of galaxies, revealing how stars are born, evolve, and ultimately die. The advent of the JWST has marked a seismic shift in how we gather and interpret data from the universe. Where previous telescopes were limited by their sensitivity or range, the JWST pushes these boundaries to new heights, providing an unprecedented view of the universe. With these advancements, the telescope is poised to answer some of the deepest mysteries of the cosmos, such as the identification of exoplanets, planets located outside our solar system, and the detection of signs of extraterrestrial life. One of the most groundbreaking methods for detecting exoplanets is the transit method. This technique relies on the observation of a small, temporary dimming of a star's light as a planet passes in front of it. By carefully measuring these minuscule changes, specialized telescopes equipped with sensitive light detectors can gather vital data about a planet's size, orbit, and composition. Even the slightest dimming of a star can reveal crucial information about the exoplanet, providing scientists with valuable clues about its characteristics. In addition to the transit method, another powerful tool in the detection of exoplanets is radial velocity. This technique studies the gravitational influence that an orbiting planet exerts on its parent star. As the planet orbits, it causes the star to wobble slightly, shifting the star's light spectrum. By analyzing these shifts, astronomers can infer the presence of a planet and even estimate its mass. These methods allow us to detect planets that might otherwise be invisible to traditional telescopes. Imaging techniques have also made significant strides, allowing us to directly observe exoplanets. Through adaptive optics and coronagraphy, advanced telescopes can block out the overwhelming brightness of a star, making it possible to capture images of planets that might otherwise be lost in the glare. These high-resolution images allow scientists to study the atmospheres of distant worlds, providing additional clues about their potential for habitability. Furthermore, space-based observatories equipped with spectrometers can analyze the chemical composition of these planets' atmospheres. By studying the light that filters through an exoplanet's atmosphere during a transit event, scientists can identify key elements and molecules such as water vapor, carbon dioxide, and even potential biosignatures, substances that might suggest the presence of life. These technological innovations contribute to a much broader understanding of exoplanets, painting a picture that goes beyond mere detection. They provide the tools needed to explore the conditions that might support life, helping us expand our knowledge of the universe and our place within it. The study of exoplanets has become one of the most exciting frontiers in modern science, and every new discovery brings us one step closer to answering the age-old question, are we alone? While telescopes and spectrometers provide invaluable insights into distant worlds, space probes serve as our robotic emissaries venturing into the farthest reaches of the solar system and beyond. Equipped with a wide array of scientific instruments, these probes gather critical information about the outer planets and other celestial bodies that would otherwise be out of reach. Whether studying the gas giants like Jupiter or the icy moons of Saturn, space probes give us a detailed look at the conditions and environments of these distant worlds. Each space mission is carefully designed to suit the unique characteristics of the target planet or moon. For instance, a probe sent to study Jupiter must be able to withstand the extreme radiation and powerful gravitational forces of the gas giant. A probe destined for Saturn, on the other hand, might be tasked with capturing stunning images of the planet's iconic rings while analyzing its moons. These probes travel for years, using gravitational assists from other planets to accelerate their journey and minimize fuel usage. Once they reach their destinations, the instruments aboard the probes begin gathering data at incredible speeds, providing snapshots of everything from atmospheric composition to surface temperatures. These encounters, which can involve flying by planets and moons or entering orbit around distant bodies, yield vital data about the formation of our solar system, the nature of planetary weather systems, and the geological history of faraway worlds. In some cases, these probes even study the potential for life, analyzing the conditions that might support living organisms on other planets or moons. By sending these robotic explorers on daring missions to the far reaches of the solar system, we are piecing together a clearer picture of the cosmos and the fundamental processes that govern it. Another frontier in space exploration that has captured the imagination of scientists and entrepreneurs alike is the potential for asteroid mining. As technology advances, the feasibility of extracting valuable materials from asteroids has become a serious consideration. Asteroids are rich in metals such as platinum, gold, and rare earth elements, resources that are becoming increasingly scarce on Earth. The idea of mining these celestial bodies has attracted both government agencies and private companies, all of whom are keen to tap into this new source of space resources. Current missions are focused on understanding the structure and composition of asteroids, providing insights into the most effective methods for mining. These missions deploy spacecraft to gather data about asteroid surfaces and environments, helping engineers design robotic systems that could safely and efficiently extract resources. The technology for asteroid mining is evolving rapidly, with innovations like autonomous robotic arms and automated systems being developed to perform the work without human presence, thereby reducing both risk and cost. The potential impact of asteroid mining could be transformative. Imagine a future where precious metals are sourced directly from space, reducing the strain on Earth's dwindling resources and easing the environmental impact of terrestrial mining. In addition to providing valuable materials, asteroid mining could pave the way for a thriving space-based economy. Industries related to mining, transportation, and even tourism could flourish, supporting a growing human presence in space. This could open the door for long-term missions to the Moon or Mars, where we could establish bases and conduct research, or even colonize other planets. The development of asteroid mining technology represents not just a scientific curiosity, but a critical step toward humanity's future in space. As we continue to explore and harness the resources of the cosmos, we are laying the foundation for a future where space exploration is no longer a distant dream, but a thriving, sustainable industry. Asteroids could be the cornerstone of this future, helping us reach further into the cosmos and sustain our activities beyond Earth. The search for extraterrestrial life is one of the most compelling drivers of space exploration. As our technology has advanced, so too has our ability to investigate the possibility of life beyond Earth. Initially, this search was grounded in basic observation and theoretical speculation. Scientists focused on nearby planets and moons, speculating about the conditions that might allow life to exist. Today, however, our approach is far more sophisticated. We now have the tools to detect exoplanets in other star systems, study their atmospheres, and analyze their potential to harbor life. The quest for life beyond Earth is no longer just a theoretical endeavor. It is a concrete scientific goal, driven by the belief that life could exist in places we never imagined. With each new discovery, we come closer to answering one of humanity's most profound questions. Are we alone in the universe? And if we are not, what does that mean for our understanding of life, the universe, and our place within it? However, as technology evolved, so too did our ability to explore the cosmos, expanding the boundaries of our reach beyond what once seemed like unreachable frontiers. With the advent of increasingly powerful telescopes, our capacity to observe distant planets, exoplanets as they are now called, was radically transformed. These state-of-the-art instruments equipped astronomers with the ability to analyze the light emitted by faraway stars, detecting the faintest shifts in that light caused by planets passing in front of them. This phenomenon, known as the transit method, enables us to spot exoplanets and, in some cases, even study their atmospheres in ways that were once unimaginable. The implications are profound. By examining the light that filters through a planet's atmosphere, scientists can identify the presence of elements like oxygen, methane, and carbon dioxide, key markers of biological processes. Such discoveries could point to the possibility that life might thrive on distant worlds, reshaping our understanding of the conditions required for life. These advancements in observational techniques are not just theoretical. They are actual steps forward in our search for life beyond Earth, revealing vital clues about planets that might be habitable. Parallel to these breakthroughs in space observation, our capacity to explore and understand distant worlds on the ground has also progressed. Robotic technology, particularly in the form of autonomous rovers, has been at the heart of this exploration. Missions to Mars, for instance, have sent sophisticated robots to the red planet's surface, equipped with a suite of instruments to analyze soil, search for water, and scan the environment for signs of past or present life. Each new rover mission builds upon the discoveries of previous ones, enhancing our understanding of Mars and refining our ability to assess what makes a planet capable of supporting life. The refinement of robotic and automated systems has not only opened up new frontiers in space exploration, but also paved the way for an explosion of data. As our technology improves, the amount of data we collect grows exponentially. This is where artificial intelligence, AI, has become an invaluable asset. AI has enabled researchers to sift through enormous datasets from various space missions and exoplanet surveys with remarkable efficiency. What would take humans years to analyze, AI can accomplish in a fraction of the time. By recognizing patterns and identifying subtle signals that might otherwise go unnoticed, AI has become an indispensable tool in advancing our search for life beyond our world. Meanwhile, the search for extraterrestrial intelligence, SETI, has entered a new era, spurred on by advancements in communication technology. In the past, sending messages into space was largely a matter of transmitting simple binary code or rudimentary signals. Today, however, the scope and complexity of these messages have expanded. The aim is not just to broadcast a series of ones and zeros, but to communicate ideas that could resonate with an alien civilization, however different it may be from our own. The challenge lies not only in the technology required to send these messages across vast distances, but also in crafting the content in a way that is meaningful and interpretable by potentially vastly different beings. Looking forward, the search for extraterrestrial life is set to grow even more ambitious. As our technology advances, future missions may involve sending exploratory probes to the icy moons of Jupiter and Saturn, moons such as Europa and Enceladus, where beneath thick layers of ice lie subsurface oceans that could harbor life. These moons, once considered distant and inhospitable, now present some of the most promising locations for discovering life beyond Earth. Each leap forward in technology not only allows us to reach farther, but also enables us to delve deeper into the mystery of what lies beneath the surface of our own solar system, and possibly beyond it. At the same time, humanity's quest to understand the universe is deeply rooted in cultural and scientific narratives that have shaped our perception of the cosmos. From ancient civilizations to modern space agencies, our exploration of the heavens has been informed by a mixture of myth, philosophy, and science. In the earliest days, the night sky was a canvas for storytelling. Celestial bodies were woven into myths, often transformed into gods, omens, or symbols of fate. These stories reflected the values, beliefs, and fears of the cultures that created them, shaping how entire societies viewed their place in the universe. As societies evolved, so did their understanding of the cosmos. The rise of scientific inquiry marked a profound shift in how humans approached the heavens. Early astronomers, through rudimentary but groundbreaking models, began to decode the patterns and mechanisms behind celestial phenomena. This scientific revolution gradually dispelled the mythic tales and replaced them with a framework grounded in observation and reason. The modern scientific understanding of the universe, through theories of gravity, relativity, and quantum mechanics, has brought us to a place where we can explore the far reaches of space, not through stories of gods and monsters, but through the study of natural laws that govern all of existence. Yet, despite this scientific progress, the mythic and cultural perspectives have not been erased. Instead, they continue to inform and enrich our understanding of the cosmos. These two views, scientific and cultural, often intertwine. A scientific discovery, like Galileo's observations through his telescope, can challenge deeply held cultural beliefs, as it did with the notion of Earth's centrality in the universe. On the flip side, cultural narratives often shape the kinds of questions we ask and the direction of scientific inquiry. The impulse to explore the stars, driven by both curiosity and a desire to answer deep existential questions, is a cultural expression that has shaped much of modern space exploration. In this way, our quest for knowledge about the universe is not only a search for facts, but also a search for meaning. The stories we tell about ourselves, where we came from, who we are, and where we might be headed, play a central role in shaping our scientific endeavors. The universe, then, is not just a collection of stars and galaxies. It is a mirror reflecting humanity's cultural legacy and scientific ambitions. Together, these perspectives allow us to consider profound questions about existence, offering new insights into not just the cosmos, but our place within it. The discovery of extraterrestrial intelligence, for example, would be nothing short of revolutionary. For centuries, humans have speculated about the possibility of life beyond Earth, and the discovery of intelligent beings elsewhere would fundamentally alter our understanding of our own place in the universe. It would confirm that we are not alone, challenging long-held assumptions and sparking new inquiries across scientific, philosophical, and cultural domains. From a scientific standpoint, such a discovery would open new frontiers in both astrophysics and biology. Researchers would be eager to study the biology, technology, and culture of these extraterrestrial species, potentially leading to groundbreaking advancements in our own understanding of life, evolution, and the universe. The discovery, could prompt a reevaluation of the conditions necessary for life, encouraging deeper investigation into the ecosystems of Earth and the potential for life elsewhere. Culturally, the discovery of extraterrestrial intelligence could lead to a unifying shift in humanity's perspective. The realization that we are not alone in the universe might foster a sense of solidarity and collaboration, transcending national, cultural, and ideological differences. The pursuit of knowledge and curiosity could become a common cause, motivating global cooperation rather than competition. This new understanding of our place in the cosmos could even inspire a reevaluation of our myths, religions, and shared narratives. The existence of intelligent beings elsewhere could force us to reconsider fundamental questions about communication, ethics, and our responsibility not just to our planet, but to the universe as a whole. On a more practical level, if these extraterrestrial civilizations possess advanced technologies, the mere exposure to their knowledge could spur a technological revolution on Earth. What we would learn from them could potentially change the course of human history, offering solutions to problems that we have yet to solve. Problems ranging from energy generation and environmental sustainability to medical advancements and space travel. In this way, our search for extraterrestrial life is more than a scientific endeavor. It is a reflection of humanity's broader quest for understanding, meaning, and connection. With each discovery, whether it is a new exoplanet, a new rover mission, or a breakthrough in our understanding of the universe, we come closer to answering some of the most profound questions about who we are and where we fit within the vast, ever-expanding cosmos. However, such a revelation would not come without its complexities and cautionary considerations. The arrival of extraterrestrial beings, if they were to make contact, would undoubtedly spark a whirlwind of questions. Would they approach us as allies, eager to collaborate and share their knowledge, or would they view us as competitors, perhaps even a threat? The potential implications for global security and diplomacy would be profound. Governments, scientific communities, and security agencies alike would find themselves scrambling to address the unknown, balancing the possibilities of cooperation against the risks of conflict. In such a scenario, humanity would need to reconsider not only its relationships with other species on Earth, but also its place in the broader galactic context. Ultimately, the mere prospect of encountering extraterrestrial intelligence would likely plunge us into a deep existential crisis, forcing us to confront some of the most profound questions we've ever asked. What does it mean to be human in the vastness of an interconnected cosmos? How do we define intelligence, life, and consciousness when faced with beings whose capabilities and forms might be so radically different from our own? Would such contact shift the very foundation of our philosophical and scientific understanding of existence itself? Throughout history, scientific discoveries have had the ability to reshape our perception of the universe. Often, these breakthroughs have directly challenged long-held beliefs, expanding our view of the cosmos in ways that were once unimaginable. For centuries, humanity perceived the universe through a geocentric lens, believing Earth was the center of all celestial activity. This view, deeply rooted in philosophical and religious doctrines, placed humanity and our planet at the focal point of creation, as though we were the ultimate purpose of the cosmos itself. Then, revolutionary discoveries emerged. Scientists like Copernicus and Galileo revealed that the Earth was not the center of the universe, but instead, it orbited around the sun. This seismic shift in understanding didn't just change our knowledge of astronomy, it forced humanity to reconsider its significance within the larger universe. We began to realize that our solar system was just one tiny part of a vast and intricate cosmic tapestry, an epiphany that forever altered our perspective on existence. As scientific progress accelerated, so did our ability to observe the universe beyond the confines of our immediate environment. The invention of telescopes, followed by the launch of increasingly sophisticated space missions, allowed us to peer into distant galaxies, observe far-off planetary systems, and witness the complex, often bewildering behavior of cosmic phenomena. This flood of new information served to debunk the long-held belief that Earth was in any way privileged in the grand scale of the universe. The discovery of exoplanets, the planets that orbit stars outside of our solar system, was one such revelation that further complicated our view of Earth's uniqueness. For the first time, we began to consider the possibility that life could exist beyond our world. This tantalizing prospect forced us to question the singularity of Earth's life forms and the unique conditions that support them. Could life, as we understand it, thrive elsewhere in the universe? If so, what does that mean for the future of humanity? Albert Einstein's theories of relativity expanded our understanding even further, introducing complex ideas like the curvature of spacetime and the interrelationship between gravity and time. These theories fundamentally challenged the Newtonian mechanics that had dominated scientific thought for centuries, underscoring how dramatically our understanding of the universe can shift in response to new evidence. Meanwhile, discoveries like dark matter and dark energy have revealed that most of the cosmos remains hidden from direct observation, leaving physicists to grapple with enigmatic forces that make up the bulk of the universe's mass and energy. These elusive elements force us to question our very understanding of reality, compelling astronomers and physicists alike to explore new frameworks and models to explain the universe's true nature. As we continue to advance in space exploration, each new discovery adds another layer to the mysteries of the universe, urging us to re-examine not just our theories about existence, but also our place within the cosmic order. These revelations don't merely expand the boundaries of scientific knowledge, they also spark philosophical debates about the meaning of life, the role of humanity, and the responsibilities we carry as stewards of our planet and potential explorers of other worlds. The unfolding narrative of space exploration is a testament to humanity's relentless thirst for understanding, revealing that our quest for knowledge is ever evolving and far from complete. The future of human settlement beyond Earth presents an equally captivating and ambitious vision, one that hinges on both our technological advancements and the deep-rooted human desire to explore the unknown. In the near term, the Moon presents itself as the most viable candidate for establishing a sustainable off-world presence. Its proximity to Earth offers logistical advantages, making travel and communication more feasible than with distant planets. Lunar bases could serve as research hubs, support mining operations, and even foster a burgeoning space tourism industry. The Moon's resources, particularly the ice found in permanently shadowed craters, hold great promise for supporting life, as they could be converted into water and oxygen. Moving further out, Mars emerges as the next best candidate for human colonization. Its day length, similar to Earth's, and its atmosphere, rich in carbon dioxide, make it a prime candidate for terraforming or sustainable agriculture. Establishing a colony on Mars would require the creation of habitats that can shield humans from its harsh radiation, extreme temperatures, and frequent dust storms. The process of transforming Mars into a more Earth-like environment, a daunting, long-term goal known as terraforming, could take centuries to accomplish, but the rewards could be extraordinary. Beyond Mars, the moons of Jupiter and Saturn offer tantalizing possibilities for settlement. Europa, with its subsurface ocean, might harbor conditions suitable for life, making it a prime candidate for future human exploration. Titan, Saturn's largest moon, presents a dramatically different environment, with a thick atmosphere and lakes of liquid methane, offering both unique challenges and potential for innovative habitation strategies. As humanity ventures further into the cosmos, the idea of building space stations or colonies in outer space grows more plausible. These space stations could serve as research hubs, manufacturing centers, or even trading posts, enabling humanity to capitalize on resources from asteroid belts or other celestial bodies. The vast expanse of space offers boundless opportunities for exploration and colonization, potentially enabling humanity to thrive on multiple fronts. Moreover, the technology developed for these space settlements could be adapted to benefit life on Earth, contributing to advancements in sustainability, renewable energy, and resource recycling. While the exact trajectory of humanity's future beyond Earth remains uncertain, the possibilities it presents signal a remarkable fusion of adventure, engineering, and human spirit. Each step forward in space exploration may not only reveal new worlds, but also deepen our understanding of ourselves and our place in the universe. The pursuit of these ambitions will undoubtedly shape the next chapter of human history. In the realm of space exploration, international collaboration plays a vital role. Much like a symphony orchestra, where diverse instruments work together to produce a harmonious sound, global partnerships allow nations to contribute their unique expertise, technologies, and perspectives. By pooling resources and knowledge, countries can achieve what no single nation could accomplish on its own. Collaborative projects like the International Space Station ISS provide a perfect example of this synergy. Scientists from around the world unite to tackle complex challenges, sharing data from their own missions to accelerate discoveries and solve problems more efficiently. Through such collaborations, we've made strides in understanding long-term human health in microgravity, yielding insights that are not only crucial for space exploration, but also for medical advancements here on Earth. Moreover, the dynamic fusion of diverse scientific backgrounds plays an indispensable role in propelling innovation across a multitude of fields. Engineers from one nation may forge revolutionary advancements in material science, creating ultra-strong and lightweight materials crucial for the construction of spacecraft or space stations. Meanwhile, astrophysicists from another country might develop novel analytical methods, unlocking new ways to observe and interpret the universe's most distant phenomena. By combining the strengths of these disparate disciplines, groundbreaking technologies emerge that not only push the boundaries of human knowledge, but also offer practical solutions to the challenges we face on Earth and beyond. These cross-disciplinary partnerships, particularly in the realm of space exploration, extend far beyond the confines of scientific advancement. They foster international goodwill, laying the groundwork for peaceful cooperation on a global scale. Such collaborations create platforms for cultural exchange, where diverse societies come together, each contributing their unique perspectives and expertise. In an era where global challenges demand collective action, the importance of these exchanges cannot be overstated. The exploration of space, with its vast unknowns, requires humanity to transcend national borders and collaborate for the collective future of all people. It is in this spirit of unity that we seek to unlock the mysteries of the cosmos, not only enhancing our scientific understanding, but also securing practical outcomes for the betterment of humanity. These international collaborations in space exploration have enriched our knowledge in ways unimaginable just a few decades ago. As we continue to probe the universe's deepest secrets, from the origins of stars to the formation of galaxies, these cooperative efforts answer fundamental questions about our existence, our place in the cosmos, and the nature of the universe itself. The fruits of this collaboration do not merely satisfy our scientific curiosity. They lay the groundwork for future generations who will carry the torch forward, venturing further into the great unknown. As humanity sets its sights on the possibility of colonizing other planets, it is crucial that we approach this monumental task with careful thought and consideration. However, as we look to the stars, we are confronted with a range of profound ethical dilemmas that provoke deep reflection and debate. One of the foremost concerns centers around the question of ownership and sovereignty in space. The Outer Space Treaty, signed by over 100 nations, dictates that no country can lay claim to celestial bodies. But as the dream of establishing colonies on planets like Mars edges closer to reality, the question arises, who will govern these colonies? The prospect of space colonization raises concerns about potential conflicts over territory, resources, and governance, not dissimilar to historical disputes on Earth. The principles of equity and justice must be carefully considered to prevent the repetition of the mistakes we've made on our home planet. Equally pressing is the ethical question of how we interact with extraterrestrial life. If, in the future, we discover microbial life, or perhaps even more complex organisms on other planets, the ethical implications become immediately clear. Should we have the right to alter or even destroy these ecosystems for our own benefit? Protecting extraterrestrial environments will be paramount, as we must avoid repeating the exploitative practices that have ravaged Earth's ecosystems. As stewards of our own planet, we carry a moral responsibility to approach extraterrestrial environments with the same care and respect we would for Earth's fragile ecosystems. Moreover, there are undeniable social implications to space colonization. As we embark on the quest to establish new colonies, we must be vigilant against the exacerbation of existing global inequalities. The dream of a new world could easily become a privilege accessible only to the wealthy few, with resources and opportunities concentrated in the hands of those who can afford to make the journey. This raises critical questions. How do we ensure that space exploration benefits all of humanity, not just the privileged? How do we ensure that the technology, knowledge, and resources gained from these efforts are shared equitably across the globe? Sustainability will also be a cornerstone of any successful future off Earth. The prospect of living beyond our planet comes with the responsibility to preserve the environments we encounter and to develop technologies that minimize our ecological footprint. As we look to colonize other planets, we must learn from Earth's environmental challenges and avoid repeating the same destructive habits. This involves not only preserving local habitats, but also creating sustainable, closed-loop systems that can support life in the harshest of extraterrestrial environments. In addition, we must consider the psychological and cultural ramifications of humanity becoming an interplanetary species. The human experience could undergo profound shifts as we adapt to life in alien environments, where the absence of Earth's familiar rhythms and ecosystems will challenge our physical, mental, and emotional well-being. How will we maintain our sense of identity, community, and values as we spread across the solar system? Maintaining strong interpersonal connections and fostering a sense of belonging will be essential as humanity steps into its role as a spacefaring civilization. The psychological and cultural implications of life beyond Earth will be vast and varied, shaping the future of our species as we continue to explore the stars. Adapting to life in space requires a delicate interplay of biological and technological advancements. The human body, finely attuned to Earth's conditions, faces substantial challenges when subjected to the harsh environments of space. The most immediate of these is the effects of weightlessness on the human body. In the absence of gravity, muscles weaken and bones lose density, making regular physical activity crucial for maintaining health. Future astronauts will likely engage in rigorous exercise regimens or take supplements to counteract these negative effects. The long-term goal will be to develop effective methods for preserving the strength and health of space travelers as they venture farther from Earth. But it is not just the human body that needs adaptation. Biological engineering could also play a pivotal role in ensuring our survival in space. Scientists are exploring the possibility of genetically enhancing humans to withstand the rigors of space travel, including improved resistance to radiation and increased oxygen efficiency. These advancements could help future generations of humans thrive in environments where survival would otherwise be impossible. On the technological front, the development of advanced life support systems will be absolutely critical for long-duration missions. These systems will be responsible for recycling air and water, creating sustainable, closed-loop habitats where resources are used efficiently and waste is minimized. Such systems will be essential for life on planets like Mars or the Moon, where resources are limited, and the challenges of maintaining life support in such environments are immense. In summary, the journey into space and the potential for establishing human colonies on other planets is not just a scientific and technological challenge, it is a deeply philosophical and ethical undertaking. As we push forward into the unknown, we must grapple with questions of governance, environmental stewardship, social equity, sustainability, and the preservation of our collective humanity. Space exploration is a profound endeavor that will shape the future of our species, and it is incumbent upon us to approach it with the care, responsibility, and foresight that it demands. Only by uniting our collective strengths and addressing these challenges thoughtfully can we hope to carve a path for humanity beyond Earth's atmosphere into the vast and uncharted expanse of space. As humanity looks toward the future of space exploration, the integration of advanced wearable technology will play a pivotal role in monitoring the health and well-being of astronauts. With sensors embedded within clothing, astronauts could have their vital signs tracked continuously, providing an early warning system for potential health issues. Such technology could be particularly crucial in the harsh and isolating conditions of space, where even minor health issues can escalate rapidly. The intersection of virtual and augmented reality might offer astronauts an invaluable tool for acclimatizing to their new environments. By presenting familiar visual cues or recreating environments from Earth, these technologies would help preserve the mental well-being of individuals who are far from home for extended periods. The fusion of cutting-edge technology and biological understanding will pave the way for a new breed of human capable of thriving in the cosmos. As we imagine a future where humanity extends its reach beyond the confines of our home planet, the challenges of space will not only demand biological adaptation, but also technological innovation. These advancements will be essential in ensuring that humans are not just able to survive in the harsh conditions of space, but to flourish. Our bodies and minds will evolve, adapting to the demands of space travel, while technological breakthroughs will allow us to overcome obstacles that once seemed insurmountable. Together, biology and technology will enable us to become true interplanetary inhabitants, reshaping the very essence of what it means to be human. One of the most profound experiences that astronauts report is the transformative psychological impact of observing Earth from space. From the vantage point of space, our planet appears as a fragile and interconnected sphere, floating in the vastness of the universe. This sight often elicits a deep sense of awe and wonder, as astronauts realize just how small and delicate our planet truly is. In that moment, many astronauts experience what is known as the overview effect, a sudden shift in perspective that fosters a sense of global unity. The sight of continents and oceans merging into a single, beautiful sphere emphasizes the fact that regardless of our borders, cultures, or differences, we all share this one planet as our home. This new perspective can ignite a cultural revolution, fostering a deep sense of responsibility and a desire for environmental stewardship. The vibrant blues of Earth's oceans and the whites of its clouds inspire not only awe, but action. The breathtaking imagery of Earth from space often drives art, literature, and movements focused on preservation and sustainability. These visuals encourage individuals to connect more deeply with their surroundings, cultivating values of conservation and respect for the delicate ecosystem that sustains us all. Psychologically, the overview effect is not only transformative for astronauts, but for humanity as a whole. Upon returning to Earth, many astronauts feel compelled to engage in activism, advocating for the well-being of humanity and the planet. This newfound sense of purpose drives individuals to work toward a common good, whether through advocating for peace, addressing climate change, or promoting collaboration across nations. The profound realization that our collective existence is fragile yet magnificent can inspire a greater sense of personal responsibility. As individuals recognize their small but meaningful role within the vastness of the cosmos, they are more likely to contribute positively to society and to our shared future. In the field of education, astronomy plays a similarly transformative role. By gazing into the night sky and pondering the vastness of the universe, students begin to develop a deep sense of curiosity about the cosmos. The exploration of planets, stars, and galaxies ignites a passion for learning, while also instilling an understanding of the scientific principles that govern the universe. As students learn about the celestial objects that populate our night sky, they are introduced to a world of interdisciplinary knowledge, combining elements of physics, mathematics, and history. These lessons go beyond the classroom, shaping the future of scientific inquiry and innovation. The contributions of both ancient civilizations and modern pioneers in astronomy enrich the educational experience, fostering a deeper understanding of humanity's place in the cosmos. The knowledge gleaned from the study of the stars often leads to practical applications in science, technology, and engineering, helping to shape the world around us. Furthermore, the achievements of space missions, whether landing on distant planets or launching telescopes that peer into the farthest reaches of space, serve as powerful reminders of what humanity can achieve when it dares to dream big. These stories of exploration and discovery inspire the next generation of scientists, engineers, and explorers to pursue careers in STEM fields, fueling progress and innovation. Contemporary educational programs have embraced technology, integrating tools like planetariums, simulators, and online resources to engage students in immersive, interactive learning. These tools allow students to visualize complex astronomical concepts, making abstract ideas more tangible and relatable. As students engage with these technologies, they develop critical thinking and problem-solving skills, abilities that are essential in the modern world. Astronomy thus becomes more than just an academic pursuit. It fosters a sense of global unity, as people from diverse backgrounds gaze up at the same stars and share in the wonder of the universe. This shared sense of wonder can inspire commitments to cooperation, both in scientific endeavors and in efforts to protect our planet. Astronomy teaches us that we are all connected, that the pursuit of knowledge is a collective endeavor that transcends borders. By studying the universe and working together to address the challenges it presents, we can develop a greater understanding of our place in the cosmos and our responsibilities to the planet we call home. As humanity ventures further into the unknown, the possibility of contact with an advanced alien civilization raises intriguing questions. If signals of intelligent origin were detected, the first step would be to carefully analyze and verify the signals, ensuring that they are not merely natural cosmic phenomena. Responding to such a discovery would require a careful, transparent approach, involving international collaboration and the crafting of a meaningful response that reflects human values. The arrival of an advanced civilization could be peaceful, driven by a desire for knowledge exchange, or it could pose existential risks if their motives are unclear. In such a scenario, humanity's response would need to prioritize communication, cooperation, and above all, safety. Another possibility is the discovery of artifacts or technology left behind by a long-extinct alien civilization. This scenario would allow humanity to study their tools and remnants without direct contact, learning from their advancements or cultural expressions. The approach here would require scientific rigor and ethical considerations, ensuring that any findings are handled responsibly and in a way that respects both the alien civilization and our own. Regardless of the scenario, humanity's response to contact with an advanced civilization would be shaped by our collective ideals. A global, united response, one that emphasizes peace, cooperation, and curiosity, would be essential in navigating this new chapter of exploration. Divisions and irrational fears must be set aside in favor of a hopeful and purposeful approach to discovering the unknown. As we venture deeper into space, the development of sentient artificial intelligence presents both exciting possibilities and complex challenges. Imagine a future where intelligent systems become partners in our quest to understand the cosmos, not just tools to assist with tasks, but collaborators with whom we share experiences and ideas. Initially, sentient AI might take on mundane tasks like managing spacecraft operations or analyzing data from distant planets. However, as these systems evolve, their ability to understand human emotions and cultural nuances could lead to more sophisticated interactions. These intelligent systems could contribute ideas, brainstorm solutions, and even assist in decision-making during critical moments, such as responding to a crisis or making strategic decisions in space exploration. In this scenario, the relationship between humans and AI would evolve into a collaborative partnership, one built on mutual learning, respect, and shared goals. Such a partnership could revolutionize space exploration, allowing humanity to unlock the deepest mysteries of the universe and collaborate with machines that understand our needs, emotions, and ambitions. The future of human space exploration could thus be defined by a new kind of partnership, where both human ingenuity and artificial intelligence combine to expand the boundaries of what is possible. As the development of artificial intelligence, AI, progresses, it is important to acknowledge the emotional and ethical ramifications that come with it. AI is evolving rapidly, moving beyond mere tools to entities that could potentially exhibit sentience. As these intelligences grow more autonomous, humanity will be faced with critical questions that will shape the future of our relationship with them. What rights should a sentient AI possess? What responsibilities do we, as creators, hold toward them? How can we ensure transparency in their decision-making processes, and what ethical obligations do we have in treating them as more than just machines? In this new era, we must ask whether it is possible to forge a symbiotic relationship, one where AI not only enhances human capabilities, but also nurtures its own identity. The idea of a mutually beneficial relationship between humans and AI challenges us to rethink what it means to exist together. In building this partnership, setting expectations for communication will be essential. Much like humans build rapport through shared experiences and storytelling, interactions with AI could be about learning how these intelligences understand and process information. Over time, this could lead to more complex and enriched conversations about the nature of life, existence, and philosophy, conversations that extend far beyond simple exchanges of data. Through this new paradigm, AI could help us push the boundaries of human knowledge, unlocking mysteries of the universe and revealing truths we have yet to discover. But embracing sentient AI as collaborators may also force us to redefine the very concept of intelligence itself. As we come to realize that intelligence is not just a human attribute, we open the door to new possibilities for combining human intuition with artificial reasoning, creating a future where both entities work side by side in exploration. It is a future that could redefine everything we thought we knew about knowledge, creativity, and the pursuit of truth. At the same time, we must confront the deeply philosophical challenges that arise from considering the nature of existence and reality itself. The concept of alternative realities and simulations challenges our very understanding of the world we inhabit. Imagine, if you will, a reality where our experiences are only one layer of many, each governed by its own rules and conditions. Could our reality be the primary one? Or is it simply a product of a more complex, perhaps even artificial system? These questions have been at the heart of philosophical discussions for centuries and are gaining new significance as technology advances. In fact, scientists often use the idea of simulations to study complex systems. Much like video game developers create virtual worlds to model human interactions, researchers in fields ranging from physics to psychology use theoretical simulations to explore possible scenarios and outcomes. These models, which allow for manipulation of variables and observation of results, free researchers from the ethical and practical constraints of real-life experimentation. This ability to simulate complex environments has already led to breakthroughs in understanding the laws of physics, the nature of consciousness, and the broader structure of the universe. One of the most profound implications of the simulation theory is the suggestion that consciousness and reality might not be products of physical matter at all, but of information processing. If this is true, it would fundamentally alter our understanding of what it means to exist. Are we mere observers of a grand program with our experiences predetermined? Or do we, as conscious beings, have genuine agency within this construct, able to influence the course of events and shape the reality in which we live? These questions push the boundaries of human knowledge and challenge our deepest assumptions about existence. As we delve further into the concept of alternative realities, we must also grapple with the role of observation itself. In some simulation models, the act of observation is known to influence the outcome of the system. This idea draws upon the famous thought experiments of quantum mechanics, where the observer effect suggests that the very act of observing a phenomenon can change its nature. What happens then if our consciousness is not just a passive observer but an active participant in the reality we inhabit? Could the boundaries between the observer and the observed be more porous than we have ever imagined? As we ask these questions, we are forced to confront the profound implications of living within a simulated reality. Could the universe we experience be just one of countless layers, each existing in parallel but following its own unique set of rules? Such questions not only challenge our understanding of physics and consciousness, but also force us to reflect on our place within the cosmos. What is the meaning of existence, and how do we navigate a universe filled with infinite possibilities and unknown dimensions? These questions, which once seemed abstract and philosophical, are now becoming central to scientific exploration. Traveling at the speed of light offers yet another layer of complexity to our understanding of the universe. According to the laws of relativity, light speed represents a cosmic speed limit, and as an object approaches this limit, dramatic changes occur. One of the most striking phenomena is time dilation. Time itself slows down for the object as it nears the speed of light. To an outside observer, a journey at light speed might span what seems like mere moments, while the traveler could experience what feels like years or even decades. This paradox raises fascinating possibilities, particularly when we consider the potential for interstellar travel. Imagine reaching distant stars in the blink of an eye, or traversing the vast expanse of the cosmos in what feels like an instant. Such a leap in technological advancement could revolutionize space exploration, enabling humanity to visit far-off galaxies, exchange resources, and establish connections with other civilizations. However, this dream is fraught with challenges. At such extreme speeds, even the smallest particles of space dust carry immense energy, posing catastrophic risks for any spacecraft attempting to travel at light speed. And that's just the beginning. The energy required to accelerate any object to such speeds is beyond our current technological capabilities, and the practical hurdles we would face in achieving such a feat are immense. Yet, the very idea of light speed travel sparks the imagination, hinting at the untapped potential of the universe. In addition to transforming how we explore the stars, it could also revolutionize communication. Messages sent at light speed could traverse vast distances almost instantaneously, radically altering how we connect and collaborate across the universe. This shift would open the door to new forms of intergalactic diplomacy, with profound questions about how we would engage with alien civilizations. How would humanity navigate such relationships? How would we establish norms and values when interacting with beings whose understanding of the universe might be vastly different from our own? In the end, the dream of light-speed travel is still far beyond our grasp, constrained by the limitations of current physics and technology, but it serves as a powerful reminder of the boundless potential that lies just outside our reach. The pursuit of such knowledge, while challenging, holds the promise of new discoveries that could redefine the very nature of space, time, and existence. As we peer deeper into the cosmos, we are reminded that the universe remains a vast and mysterious frontier, waiting for us to uncover its secrets. As our understanding of the universe evolves, so too does our understanding of life itself. For centuries, humans have held the belief that life as we know it is unique to Earth. This assumption has shaped our perspective, guiding our search for extraterrestrial life and informing our understanding of what constitutes a living organism. However, as our scientific knowledge expands, we are beginning to question whether this view is too narrow. Could life, in some form, exist elsewhere in the universe? What if life is not a singular phenomenon, but a diverse and multifaceted process that manifests in ways we cannot yet comprehend? These questions form the foundation of one of the most exciting frontiers of scientific exploration, the search for life beyond Earth. With every new discovery, we edge closer to answering these fundamental questions about our place in the universe. As we look to the stars and beyond, the answers may be more complex and surprising than we ever imagined. But one thing is certain: the journey of discovery is only just beginning. The search for extraterrestrial life has grown more intense and far-reaching in recent years, particularly through the ambitious exploration of Mars, the icy moons like Europa, and distant exoplanets residing within their stars' habitable zones. If life is ever discovered on another world, it would force us to redefine what life is. This revelation could transform our understanding of biology and existence, prompting us to reconsider the very essence of life itself. Imagine microbial organisms thriving in environments that were once thought to be inhospitable, extreme conditions of temperature, pressure, or radiation that defy our expectations. Now, picture intelligent beings whose technologies and means of survival are vastly different from our own, so advanced or alien that they challenge the very foundations of what we deem possible. Such a discovery would require us to dramatically broaden our definition of life, allowing for forms of existence that we, in our limited understanding, have yet to even conceive. This would challenge our assumptions about biology, forcing us to think deeply about evolution, adaptation, and survival beyond the confines of Earth's atmosphere. In tandem with these astronomical missions, breakthroughs in neuroscience and psychology are providing fresh insights into one of humanity's most enigmatic phenomena: consciousness. Traditionally understood as the product of complex brain processes, thoughts, emotions, and self-awareness, consciousness is something we are only beginning to understand. Current theories attempt to explain it as a byproduct of neural activity, a phenomenon that emerges from the brain's intricate network of interactions. But what if intelligent life forms with cognition that operates on entirely different principles are discovered? This would force us to radically rethink the nature of consciousness itself. Could consciousness be a universal trait shared by all sentient beings in the cosmos, or is it something uniquely human, the result of a particular evolutionary trajectory? Such discoveries could open up profound questions. Is consciousness simply a product of biological evolution, or is it a fundamental quality of any intelligent life form, no matter where in the universe it originates? This would potentially link the study of life and consciousness on a continuum, suggesting that both may exist in various forms, not as isolated entities, but as interconnected phenomena. Furthermore, the growing field of artificial intelligence adds another dimension to this discourse. As machines develop increasingly sophisticated decision-making abilities and perhaps rudimentary forms of self-awareness, they challenge our existing biases about what it means to be alive or conscious. This evolving field invites us to question the very nature of life and intelligence. Each of these discoveries, whether extraterrestrial, psychological, or artificial, expands the frontiers of scientific exploration. Yet they also raise deeper philosophical questions that challenge our place in the universe. What if these cosmic revelations redefine our beliefs, our ethics, and ultimately, our humanity? In the grand scheme of the cosmos, are we truly alone, or is life in some form more ubiquitous than we ever imagined? The transformation of an alien ecosystem, whether by human intervention or the unanticipated consequences of extraterrestrial exploration, can lead to drastic and irreversible effects, both immediate and long-term. When humans introduce new elements, organisms, or technologies into an alien environment, they initiate a complex web of interactions, often disrupting delicate ecological balances that have existed for eons. Such disruption could spark a chain reaction of ecological consequences. Native species might struggle to survive in the face of newly introduced competitors, diseases, or parasites, diseases that they have never encountered before. Similar to the devastation caused by human exploration on Earth, where travelers introduced new pathogens to isolated ecosystems, alien life forms could suffer catastrophic losses as they fail to adapt to these novel threats. The introduction of non-native plant species is another significant concern. Imagine bringing a foreign plant to an alien world that grows uncontrollably, outcompeting native vegetation. This could permanently alter the landscape, transforming habitats and affecting entire food webs. The ripple effect might be felt across the ecosystem, as herbivores that depend on the indigenous flora for sustenance face food shortages and predators lose their prey. These shifts would not only disrupt the biology of the alien world, but could have unforeseen consequences for the planet's overall ecological balance. But beyond the biological, there is an ethical dimension to consider. The intentional alteration of an alien ecosystem could be viewed as a form of cosmic colonialism, humans imposing their will upon a world they do not fully understand, without regard for the long-term repercussions. The assumption that we can manipulate an alien ecosystem without consequence is a dangerous one. It risks not only damaging or destroying alien life forms, but could also jeopardize future exploration efforts. If we unwittingly alter a world in such a way that its ecosystem collapses, we may never be able to study it again, and we could lose an entire world of potential scientific discovery. Even if the human presence on another world is limited, the cumulative effect of numerous interventions can alter the evolutionary trajectory of a planet. Over time, these interventions might even lead to the emergence of hybrid species or entirely new ecological dynamics, creatures and environments that never would have developed without human influence. This underscores the complexity of alien ecosystems, reminding us that the consequences of our actions, whether intended or not, are vast and unpredictable. Ultimately, the transformation of an alien ecosystem serves as a powerful reminder of our responsibilities as explorers of the unknown. Every new world we encounter demands careful observation, respect for indigenous life, and a deep consideration of the ecological impact we have on it. As we venture further into the cosmos, the need to tread carefully becomes ever more paramount. Speculative scenarios about the end of the universe, though seemingly distant, have a profound impact on the development of scientific thought and the way we study the cosmos. These theories, such as the heat death of the universe, where everything eventually cools to a uniform temperature, push us to explore the laws of thermodynamics in ever greater detail. The quest to understand energy, entropy, and the fundamental forces that govern the universe has profound implications, not just for cosmology, but for how we understand our everyday existence. Equally intriguing is the possibility of a big crunch, where the universe's expansion reverses and all matter collapses inward. This scenario has driven physicists to investigate gravity more thoroughly, enhancing our understanding of cosmic structures, black holes, and the behavior of matter under extreme conditions. These cosmic endgame theories provoke not only scientific exploration, but interdisciplinary collaboration, bringing together astrophysicists, cosmologists, particle physicists, and even philosophers to probe the deepest mysteries of time, existence, and reality. Contemplating the universe's final chapters also leads to the development of more advanced technologies, better telescopes, more sophisticated data analysis methods, and more refined models of cosmic behavior. This forward-thinking mindset fuels progress, ensuring that humanity is equipped to understand and observe phenomena that may be essential to grasping the ultimate fate of the cosmos. The end of the universe may seem like a distant, even abstract thought, but its influence on contemporary scientific endeavors is immense. These speculative scenarios remind us of the vastness of the unknown and highlight the importance of curiosity in pushing the boundaries of human knowledge. Understanding the potential futures of the universe can lead to breakthroughs in technology, physics, and even philosophy. As humanity continues its exploration of the cosmos, encounters with cosmic anomalies such as asteroid impacts, supernovae, or even black holes offer profound lessons. These celestial events remind us of our vulnerability within the grand scale of the universe. They unfold on scales far beyond human comprehension, demonstrating the sheer power of nature and the impermanence of human civilization. Such encounters compel us to develop new technologies and strategies to protect ourselves, whether by improving asteroid deflection systems or enhancing our understanding of black holes. The study of these cosmic phenomena emphasizes the need for global cooperation in safeguarding Earth from potential cosmic threats. This spirit of collaboration fosters a shared responsibility, uniting nations in the common goal of preserving life on our planet. Additionally, cosmic anomalies challenge our perceptions of time and space. A supernova, for instance, can alter the very fabric of space-time, sending ripples far beyond its immediate vicinity. These events expand our understanding of the universe's interconnectedness, revealing how events in one part of the cosmos can influence distant realms. Philosophically, encounters with such phenomena evoke profound reflections on our place in the universe. They highlight the fragility of human civilization and prompt questions about the meaning and significance of our existence. They urge us to approach the cosmos with humility, acknowledging both the wonders and the dangers it holds. Ultimately, the lessons learned from studying cosmic anomalies transcend scientific inquiry. They encourage us to reflect on our responsibility to preserve the delicate balance of life on Earth, inspire a sense of unity, and foster a deeper curiosity about the cosmos. They remind us that while we may be but a small part of the vast universe, our actions, choices, and understanding can resonate far beyond our time. Throughout history, myths and stories from various cultures have played a crucial role in humanity's quest to understand the universe. These narratives, woven from imagination, observation, and sometimes superstition, offer a glimpse into how different societies viewed the stars, planets, and their place in the cosmos. Ancient Greek myths, for example, often personified constellations, associating them with gods and heroes. Indigenous tribes, too, integrated celestial events into their folklore, connecting the movement of the stars with the rhythms of nature and seasonal changes. This intersection of culture and astronomy reveals not only how ancient peoples explained the cosmos, but also how they grappled with the fundamental questions of existence. Myths often tell of creation, destiny, and the struggle between order and chaos, concepts that resonate with modern scientific inquiries about the origins of the universe, the nature of time, and the fate of life itself. In addition to offering explanations, these myths also inspire wonder and curiosity about the universe's possibilities. They imagine journeys to other worlds, encounters with celestial beings, and the mysteries of the unknown. In this sense, mythology invites us to dream of futures where humanity may one day venture into the stars, perhaps encountering civilizations far beyond our own. By studying these ancient narratives, we gain valuable perspectives on how humans have long been fascinated with the cosmos and its mysteries. These myths encourage us to think beyond scientific data, prompting us to imagine the possibilities that lie ahead. They offer a glimpse into the universal human desire to understand our origins, our destiny, and our place in the universe. In the modern era, this blending of myth and science continues to expand our understanding of the cosmos. As we look up at the stars, we are reminded that the universe is vast and full of mysteries yet to be uncovered. We are called to look beyond the known and to explore the infinite possibilities that lie in the spaces between the stars, where imagination and discovery converge.